Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and science takes its time, wandering gently rather than rushing. Tonight, we're going to drift through one of the most fascinating subjects in astronomy, something both intimidating and strangely beautiful, something that hides in the darkness yet shapes entire galaxies. We're going to spend some quiet time with black holes. Now, that phrase can sound dramatic at first. Black holes have a reputation after all. They're often described as cosmic monsters, devourers of stars, bottomless pits in space where even light cannot escape. Films and documentaries like to show them as roaring whirlpools or glowing maws tearing apart anything that comes close. But the real universe is usually calmer than that. Vast, quiet, patient. And black holes, for all their power, are part of that quiet universe too. So rather than imagining something violent or frightening, it may help to picture black holes as deep wells in the fabric of space, still and silent, shaping everything around them in ways that are subtle most of the time, and dramatic only under certain conditions. They are not cosmic vacuum cleaners sweeping up everything nearby. In fact, most black holes spend the majority of their existence doing very little at all, simply sitting in the darkness, surrounded by stars that orbit peacefully at safe distances. Before we go any further, I'd like to ask you something gently. The same way one might ask while sitting beside a window at night. Where are you listening from right now? Perhaps you're in your bedroom, the lights low, the world outside quiet. Maybe you're travelling, listening through headphones while the hum of a train or the soft noise of distant traffic drifts in the background. Or maybe it's late afternoon where you are, and this is simply a moment of rest in a busy day. And one more small fitting question, what time is it for you right now? It's interesting, isn't it, that we can be scattered across continents, across time zones, across entire hemispheres, and yet meet here in the same quiet moment, thinking about the same distant objects that lie far beyond all of us. If you find this kind of slow exploration soothing, if it helps your thoughts settle or simply gives your mind something gentle to follow, I'd be grateful if you gave the video a like and perhaps subscribed. It helps this calm corner of science reach more people who might need a peaceful place to rest their thoughts for a while. Now, let's begin easing into the story. Black holes are among the strangest objects ever discovered, but in a way, their story begins with something very familiar: gravity. Gravity is the reason your feet stay on the ground, the reason the moon circles Earth, the reason planets follow their paths around the sun. It's the quiet force that shapes the large-scale structure of the universe, working constantly, invisibly, without hurry. Usually gravity is gentle when you notice it in daily life. A falling leaf, a dropped cup, the weight of a blanket. But gravity has no real upper limit. If enough mass gathers in one place, gravity becomes stronger and stronger, bending space itself more and more. That idea alone is already remarkable, that space is not just empty nothingness, but something that can stretch and curve like a flexible surface. Massive objects like stars and planets create gentle dips in that surface. Black holes are what happen when the dip becomes so deep that it forms a kind of well, with sides so steep that nothing inside can climb back out. It's worth pausing here and letting that idea settle for a moment, because it's easy to rush past it. A region of space where escape is impossible, not because of walls or barriers, but because the structure of space itself is curved so intensely that every possible path leads inward. And yet, even that description can make black holes sound more dramatic than they usually are. From far away, a black hole doesn't look like a spinning vortex or a glowing eye. If it isn't actively pulling in gas or dust, it can be almost invisible, detectable only by the motion of stars around it, or by subtle gravitational effects. In fact, if our sun were magically replaced by a black hole of the same mass, something interesting would happen. Earth would continue orbiting almost exactly as it does now. The seasons would vanish, of course, because there would be no sunlight, and that would be a serious inconvenience. but the orbit itself would remain stable. Gravity depends on mass, not on whether that mass is shining or dark. So black holes are not defined by some kind of cosmic hunger. They are defined by density, by matter compressed into an incredibly small volume, creating gravity so strong that the escape velocity exceeds the speed of light. That phrase, escape velocity, is simply the speed needed to break free from gravity. On Earth, rockets must reach about 11 kilometers per second to escape our planet's pull. That's fast, but still achievable with enough fuel and engineering. For a black hole, the escape velocity exceeds 300,000 kilometers per second, the speed of light itself, and since nothing can travel faster than light, nothing that crosses a certain boundary can ever return. That boundary is called the event horizon, a name that sounds technical but has a simple meaning. It's the point beyond which events cannot affect the outside universe. Anything that happens inside remains hidden forever. It's a quiet boundary. There's no flashing line in space, no sudden jolt as you cross it. If you could somehow approach a black hole safely, you wouldn't see a glowing barrier. You would simply pass a point of no return without noticing anything special at that exact moment. There's something strangely peaceful about that idea. The universe, even at its most extreme, doesn't always announce itself with drama. Sometimes the most profound boundaries are silent ones. Over the years, astronomers have discovered that black holes are not all the same. There isn't just one kind. Instead, the universe contains a whole family of black holes, ranging from ones only a few times the mass of our Sun to giants billions of times more massive, lurking at the centres of galaxies. Some formed from dying stars. Others may have formed in the earliest moments of the universe, long before galaxies existed. Some drift alone through interstellar space, while others exist in pairs, orbiting each other in slow spirals that eventually end in powerful collisions sending ripples through space itself. And that's really what makes this subject so fascinating. When we talk about black holes, we're not talking about a single phenomenon, but about many different kinds, each with its own origin, behaviour, and role in the cosmos. It's a bit like talking about oceans. At first, you might think of one vast body of water, but then you realise there are shallow seas, deep trenches, coral reefs, and currents that circle the globe. Black holes, in their own way, form a landscape just as varied. For most of human history, black holes were purely theoretical. The idea began as a mathematical curiosity. In the 18th century, long before modern physics, a few thinkers wondered whether gravity could ever become strong enough to trap light. At the time, light was thought of as tiny particles, and the question seemed almost philosophical. Then, in the early 20th century, Einstein's theory of general relativity changed everything. Gravity was no longer just a force pulling objects together, it was a curvature of space and time themselves. And within Einstein's equations, there were solutions that described regions where that curvature became extreme. At first, even Einstein himself was skeptical that such objects could exist in reality. The equations allowed them, but nature often has a way of avoiding the most extreme possibilities. For decades, black holes, as real physical objects, remained uncertain, more like mathematical shadows than astrophysical realities. It wasn't until the mid-20th century that evidence began to accumulate. Astronomers started detecting invisible companions to stars, objects that exerted strong gravitational pulls but emitted no light. Later, powerful radio and X-ray telescopes revealed energetic regions at the centres of distant galaxies, far too bright to be explained by ordinary stars. Gradually the picture became clear. Black holes were not rare curiosities. They were common features of the universe. And yet, despite everything we've learned, black holes still carry an air of mystery, not because we understand nothing about them, but because they sit at the boundary of several great areas of physics. Gravity, quantum mechanics, thermodynamics, and the nature of space and time itself all meet at the edge of a black hole. That boundary between the known and the unknown has always been a place that draws human curiosity. We're naturally interested in edges, horizons, limits, the points where understanding fades into speculation. But tonight, there's no need to rush toward the deepest mysteries all at once. Instead, we can take our time, moving gradually, beginning with the simplest and most familiar kinds of black holes, the ones formed when massive stars reach the ends of their lives. Before we get there, though, it's worth pausing for a moment to appreciate how remarkable it is that we can even know about these objects at all. Black holes emit no light. They are, by definition, dark. And yet, through careful observation, patient measurement, and a great deal of imagination, scientists have learned to detect them, weigh them, even photograph the glowing matter swirling around them. That first image of a black hole, released in 2019, was not a photograph in the usual sense. It was a reconstruction based on data from a network of radio telescopes spread across the Earth, working together like a single instrument the size of our planet. The result was a faint ring of light surrounding a dark centre, the shadow of a black hole against the glowing gas around it. It's a quiet image, almost understated, but it represents decades of effort and centuries of curiosity. And perhaps that's one of the most comforting things about science. Even the darkest, most distant objects can be understood, little by little, by minds that are patient enough to ask careful questions and wait for careful answers. Each type tells a different part of the same story. A story about gravity, matter, and the long history of the cosmos itself. To understand the many kinds of black holes that exist, it helps to slow down for a moment and look carefully at what a black hole actually is, in the simplest possible sense. The term itself can feel heavy with mystery, but at its core the idea is surprisingly straightforward. A black hole is a region of space where gravity has become so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary, as we briefly touched on earlier, is called the event horizon. It isn't a surface in the usual sense. There's no solid shell there, no barrier you could tap with your hand. Instead, it's more like an invisible threshold in space. Outside it, escape is possible. Inside it, every possible path leads inward. What makes this especially interesting is that a black hole isn't really an object in the way a planet or a star is. It's more accurate to think of it as a condition of space itself. When enough mass is squeezed into a small enough volume, gravity becomes overwhelming, bending space and time so steeply that all roads lead toward the centre. That centre is often called the singularity, a word that sounds technical, but simply refers to a point where our current understanding of physics breaks down. The equations predict that matter is compressed to an extremely small region of enormous density, but what truly happens there is still uncertain. Scientists suspect that a complete theory of quantum gravity, something we don't yet have, will be needed to fully understand it. Fortunately, for our purposes, we don't need to peer all the way into that deepest mystery. Much of what makes black holes fascinating can be understood by looking at the region around them, where gravity shapes the motion of light and matter in ways that are dramatic but still describable. One of the most helpful ways to picture this is to imagine space as something flexible rather than rigid. This isn't just a metaphor. In Einstein's theory of general relativity, space and time form a single fabric that can curve. Massive objects like stars create gentle curves in that fabric, and planets follow those curves, which is what we perceive as gravity. A black hole is what happens when that curvature becomes extreme, forming a kind of funnel so deep that the slope becomes effectively vertical at the event horizon. Beyond that point, every possible direction leads downward. It's worth noting something that often surprises people. A black hole doesn't actively suck things in from vast distances. If you were far enough away, you could orbit a black hole just as safely as you orbit a star of the same mass. Gravity depends on mass and distance, not on whether the object is a black hole or a shining star. This means that many black holes are not surrounded by swirling disks of glowing gas. Those dramatic scenes you sometimes see in visualizations occur only when a black hole is actively feeding, pulling in nearby matter that heats up as it spirals inward. In many cases, black holes exist quietly, with little happening around them at all. Another idea that helps build an intuitive understanding is escape velocity. Every object with gravity has one. It's simply the speed you would need to leave that object's gravitational pull without further propulsion. On Earth, that speed is about 11 kilometers per second. On a neutron star, which is already an incredibly dense stellar remnant, the escape velocity can be a significant fraction of the speed of light. For a black hole, the escape velocity at the event horizon exceeds the speed of light itself, and since light is the fastest thing that can travel through space, nothing inside that boundary can ever climb back out. Interestingly, the event horizon itself doesn't mark a place where gravity suddenly becomes infinite, or where conditions instantly become destructive. If you are falling toward a very large black hole, you might cross the event horizon without noticing anything unusual at that precise moment. The real dangers, such as intense tidal forces, depend on the size of the black hole. Smaller black holes have stronger tidal forces near the horizon, while larger ones can have relatively gentle conditions there, at least temporarily. Tidal forces are another concept worth understanding, because they play an important role in what happens near black holes. Gravity becomes stronger the closer you get to a massive object, and if the difference in gravitational pull between one part of an object and another becomes large enough, it can stretch that object. Near some black holes, this stretching effect becomes extreme, a process sometimes called spaghettification, which is exactly as descriptive as it sounds. The difference in gravitational pull between your feet and your head could become so large that you would be stretched into a long, thin shape. It's not a pleasant thought, but it's a good illustration of how gravity behaves in extreme environments. Fortunately, these effects occur only very close to the black hole. At safe distances, gravity behaves in a perfectly ordinary way, following the same laws that govern the motion of planets and moons. Light itself behaves in fascinating ways near a black hole. Because gravity curves space and time, it also bends the paths of light rays. This can produce effects known as gravitational lensing, where light from objects behind the black hole is bent around it, sometimes forming rings or multiple images. If you could look at the sky from near a black hole, the stars would appear distorted, stretched into arcs and circles by the curvature of space. The sky would look unfamiliar, as though the universe had been gently twisted. Time, too, behaves differently near a black hole. According to general relativity, strong gravity slows the passage of time relative to distant observers. A clock near a black hole ticks more slowly than a clock far away. This effect, known as gravitational time dilation, has been measured even in the weaker gravity of Earth, using precise atomic clocks at different altitudes. Near a black hole, the effect becomes much stronger. To a distant observer, an object falling toward the event horizon appears to slow down, its light becoming redder and dimmer, never quite seeming to cross the boundary. From the falling object's own perspective, however, it crosses the horizon in a finite amount of time and continues inward. This difference in perspective is one of the most intriguing aspects of relativity. Different observers, in different gravitational conditions, can experience time in genuinely different ways, and both perspectives are equally valid within the framework of physics. Now, you might wonder how something as extreme as a black hole can form in the first place. After all, stars are enormous, but they're also supported by internal pressure, the outward push of heat and radiation produced by nuclear fusion. For most of a star's life, this outward pressure balances the inward pull of gravity, creating a stable equilibrium, but stars do not burn forever. Eventually, they exhaust their nuclear fuel. When that happens, the outward pressure decreases and gravity begins to win. In smaller stars, this collapse stops when the matter becomes dense enough to form a white dwarf. In somewhat larger stars, it can form a neutron star, an object so dense that atoms themselves are crushed, leaving a sphere composed mostly of neutrons. If the star is massive enough, however, nothing can stop the collapse. Gravity overwhelms all known forms of pressure, and the core continues shrinking until it forms a black hole. That process, the death of a massive star, is one of the primary ways black holes are created. These are known as stellar mass black holes, and they are thought to be quite common in our galaxy. Astronomers estimate that the Milky Way may contain millions of them, most of them quiet and invisible, drifting through space or orbiting companion stars. Yet stellar collapse is only one pathway. As we move forward, we'll encounter black holes that formed through entirely different mechanisms, some growing slowly over billions of years, others possibly forming in the earliest moments of the universe itself. Before we move on to those varieties, there's one more subtle but important point to consider. A black hole is defined not by what it's made of, but by its mass, its spin, and possibly its electric charge. This idea is sometimes summarized by the phrase "black holes have no hair," meaning that all the complicated details of the matter that form the black hole are lost behind the event horizon, leaving only a few measurable properties. This simplicity is part of what makes black holes so elegant from a theoretical perspective. No matter what falls in, gas, dust, stars, or even light itself, the black hole is described by just a handful of numbers. At the same time, this raises deep questions about information and the nature of reality, questions that physicists are still working to answer. But those mysteries can wait for later. For now, it's enough to appreciate that black holes, despite their reputation, are governed by clear physical principles, understandable step by step. Another comforting thought is that black holes are not eternal in the strictest sense. According to a theory proposed by Stephen Hawking, black holes can slowly lose mass by emitting a faint form of radiation, now called Hawking radiation. Over incredibly long timescales, far longer than the current age of the universe, this process could cause black holes to evaporate. For large black holes, the rate of this evaporation is so slow that it's essentially negligible on human timescales. But the idea itself is remarkable. Even the darkest objects in the universe are not entirely silent. At the quantum level, there may be a faint whisper of energy escaping over unimaginable stretches of time. When you step back and look at the full picture, a black hole is not just a cosmic curiosity. It is a natural consequence of gravity, one of the many ways matter and energy can organize themselves under the laws of physics. And perhaps that is the most reassuring perspective of all. Black holes are not violations of nature's rules, they're expressions of those rules, taken to their most extreme limits. Long before a black hole ever exists, long before gravity tightens its grip beyond any hope of escape, there is a star. Not a small, quiet star like our Sun, but a giant, a star so massive that its life is destined to be both brilliant and brief. These stars begin the same way all stars do, as vast clouds of gas and dust drifting through space. Over time, gravity slowly gathers that material inward, pulling it together until the center becomes hot and dense enough for nuclear fusion to ignite. Once fusion begins, a star enters a long period of balance. Gravity pulls inward, trying to compress the star, while fusion in the core pushes outward, releasing energy and creating pressure. For millions or even billions of years, those two forces hold each other in check, and the star shines steadily into the darkness. But balance in the universe is rarely permanent. Massive stars live fast. Because they contain so much material, the pressure and temperature in their cores are far higher than in smaller stars. Fusion proceeds at an enormous rate, and fuel is consumed quickly. While a star like our Sun can shine for about 10 billion years, a star many times more massive might burn through its fuel in only a few million years. A brief life on cosmic timescales. At first, the fusion process is straightforward. Hydrogen nuclei fuse into helium, releasing energy. Later, when hydrogen in the core becomes scarce, the core contracts under gravity, heating up until helium begins to fuse into heavier elements like carbon and oxygen. In very massive stars, this process continues further. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and eventually silicon into iron. Each stage happens faster than the last. The fusion of hydrogen may last millions of years, helium fusion perhaps hundreds of thousands, but by the time the core is producing iron, the timescale shrinks dramatically. That final stage may last only days. Iron is the turning point. Fusion releases energy only when lighter elements combine into heavier ones up to iron. Beyond iron, fusion consumes energy rather than releasing it. So when the core of a massive star becomes mostly iron, fusion can no longer provide the outward pressure needed to resist gravity. And gravity, patient and relentless, begins to take over. What follows is one of the most dramatic events in the universe, though from far away it unfolds in near silence. The core of the star collapses, not slowly but in a matter of seconds. The inward pull of gravity becomes overwhelming, and the material in the core falls inward at tremendous speeds. To understand how sudden this collapse is, imagine a sphere larger than Earth, compressing to a much smaller size in less than a minute. The densities and temperatures rise beyond anything we can easily picture. Atoms are crushed. Electrons and protons are forced together, forming neutrons and releasing vast numbers of neutrinos, tiny particles that pass through matter almost effortlessly. In some cases, this collapse halts when the core becomes a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But if the original star is massive enough, even neutron degeneracy pressure, the force that resists further compression, cannot stop the collapse. Gravity continues to win. The core shrinks further, and once it is compressed within a critical radius, the escape velocity exceeds the speed of light. At that moment, a black hole is born. Interestingly, the formation of the black hole itself is hidden from view. The event horizon forms deep within the collapsing core, and from the outside we cannot see the exact instant it appears. What we do see is something else, something far more visible, the outer layers of the star reacting to the collapse of the core. When the core suddenly shrinks, it creates a shock wave that travels outward through the star. Combined with the flood of neutrinos released during collapse, this shock can blow the outer layers of the star into space in an enormous explosion known as a supernova. For a brief time, that single dying star can outshine an entire galaxy. These explosions scatter heavy elements into space, elements like gold, uranium, and many of the atoms that make up planets and living things. It's a curious thought that the material in our own bodies was forged in ancient stars and dispersed by explosions like these. The death of massive stars is not only destructive, it is also creative, seeding the galaxy with the ingredients for new stars, new planets, and eventually new forms of life. At the centre of that expanding cloud of debris, the black hole remains, silent and dark, a remnant of the star that once shone. Not every massive star produces a spectacular supernova. In some cases, the collapse may happen so completely that much of the star falls inward, rather than being blown outward. Astronomers sometimes call these failed supernovae, events where a massive star simply fades from view, leaving behind a black hole with little outward drama. Imagine a star visible in the night sky one year, and then, over the course of months, it dims and disappears, leaving nothing behind that can be seen with ordinary telescopes. Only careful measurements of the surrounding region might reveal the presence of a newly formed black hole. There is something almost eerie about that possibility, a reminder that not all cosmic events announce themselves with brilliant fireworks. Some endings are quiet. The mass of the original star determines the kind of remnant that forms. Stars several times the mass of the Sun may leave neutron stars, while those more than roughly 20 times the Sun's mass are more likely to produce black holes, though the exact threshold depends on many details, including the star's composition and rotation. Rotation, in fact, plays an important role. Stars are rarely perfectly still. Most rotate, some quite rapidly, and as a star collapses, its rotation speeds up, much like an ice skater pulling in their arms. This conservation of angular momentum can cause the forming black hole to spin, and that spin affects the behaviour of space and matter around it. A rotating black hole drags space itself around with it, a phenomenon known as frame dragging. But we'll explore spinning black holes in more detail later because they form an important category of their own. Another factor that influences black hole formation is the presence of a companion star. Many stars exist in binary systems orbiting a partner. When one star in such a system collapses into a black hole, the story doesn't necessarily end there. The black hole may begin pulling material from its companion, forming a glowing disk of gas that spirals inward and heats up to extraordinary temperatures. These systems, known as X-ray binaries, are among the ways astronomers first confirm the existence of stellar mass black holes. The black hole itself remains invisible, but the hot gas around it shines brightly in X-rays, revealing the presence of something compact and massive. It's fascinating to consider that many black holes in our galaxy may have formed billions of years ago and have been drifting through space ever since, mostly unnoticed. The Milky Way could contain millions of them, scattered quietly among the stars. And yet, despite their abundance, black holes formed from stellar collapse are only the beginning of the story. The universe contains black holes of many sizes and origins, some far larger than anything a single star could produce. Before we move on to those, it's worth lingering a little longer on the process of collapse itself, because it reveals something profound about the nature of gravity. Gravity is often described as the weakest of the fundamental forces, and in many ways that's true. A small refrigerator magnet can easily overcome the gravitational pull of the entire Earth on a paperclip. But gravity has one unique property: it always attracts, never repels, and because of that, its effects accumulate. Over time, gravity gathers matter, building larger and larger structures, clouds, stars, galaxies. And in the most extreme cases, gravity gathers so much matter into such a small space that it creates a black hole. There's a kind of inevitability in that process. Once a sufficiently massive core begins to collapse, and no known force can halt it, the formation of a black hole becomes unavoidable, a natural consequence of the laws of physics. It's also interesting to reflect on how brief the actual birth of a black hole is compared to the long life of the star that precedes it. A massive star may shine for millions of years, but the collapse of its core happens in seconds. An entire lifetime ends in an instant, and a new kind of object begins to exist, one that may persist for trillions of years or more. Time itself behaves differently near black holes, as we discussed earlier, but even without considering relativity, the contrast in timescales is striking. Long, slow beginnings followed by sudden dramatic endings. Astronomers continue to study supernovae and stellar collapses in order to understand these processes better. Modern telescopes can detect neutrinos from nearby supernovae, measure the gravitational waves produced when massive objects collide, and observe the remnants left behind. Each observation adds another piece to the puzzle, helping us understand not only how black holes form, but how stars live and die, how galaxies evolve, and how the elements essential to life are distributed throughout the universe. The universe is vast and sometimes violent, but it is also consistent. The same physical laws apply everywhere, from the smallest particles to the largest galaxies. Black holes are not exceptions to those laws. They are among their most striking consequences. So when we look up at the night sky and see the faint glow of distant stars, it's worth remembering that some of those stars are already gone, their light still travelling toward us across years or centuries of space. Somewhere out there, unseen black holes mark the places where brilliant suns once burned. Once a massive star has lived its brief, brilliant life and gravity finally overwhelms the forces holding it up, what remains is often a black hole that is, by cosmic standards, relatively modest in size. These are known as stellar mass black holes, and although the name may sound technical, it simply means black holes formed from individual stars. They are the most common type of black hole in the universe, and in many ways they are the easiest to understand, because their origins are closely tied to processes astronomers have studied for decades: the birth, life, and death of stars. A typical stellar mass black hole contains anywhere from about 3 times the mass of our Sun to perhaps a few dozen times that amount. That might sound enormous, and it certainly is when compared to planets or moons, but in the scale of galaxies it is quite small. The black hole at the centre of the Milky Way, for example, has a mass of about 4 million suns, far larger than anything produced by the collapse of a single star. Yet despite their smaller size, stellar mass black holes are remarkable objects. What makes them especially fascinating is the contrast between their mass and their physical size. A black hole with 10 times the Sun's mass might have an event horizon, only about 30 kilometers across, roughly the size of a city. Imagine compressing something heavier than 10 suns into a region smaller than a metropolitan area. The density involved is almost beyond comprehension, and still, from a safe distance, such a black hole would not appear dramatic or frightening. It would not glow or roar. Unless it were actively pulling in material, it would simply sit in darkness, detectable only through its gravitational influence. For a long time, this made stellar mass black holes very difficult to find. Astronomers cannot see black holes directly, because they emit no light. Instead, they must look for clues, subtle hints that something massive and invisible is present. One of the earliest and most important clues came from binary star systems. Many stars exist in pairs, orbiting a common centre of gravity. In some cases, one of those stars evolves more quickly, becoming a red giant, exploding as a supernova, and leaving behind a compact remnant. If that remnant is a black hole, the system may continue to exist, with the black hole orbiting its companion star. And here, something interesting can happen. If the two objects are close enough, the black hole's gravity can begin pulling gas away from the companion star. That gas doesn't fall straight in. Instead, it forms a swirling disk called an accretion disk, heating up as friction and compression increase its temperature. By the time the gas spirals close to the event horizon, it can reach temperatures of millions of degrees, hot enough to emit intense X-rays. These X-rays can be detected by telescopes in orbit around Earth, revealing the presence of an invisible but powerful object. One of the first strong candidates discovered this way was Cygnus X1, an X-ray source in the constellation Cygnus. Observations showed that a visible star in that system was orbiting an unseen companion with a mass far too large to be a neutron star. The most plausible explanation was a black hole, and over time additional evidence confirmed it. Discoveries like this gradually changed black holes from theoretical curiosities into real, observable objects. Today, astronomers have identified many stellar mass black holes in our galaxy, and they suspect there are millions more that remain undetected, either because they are not actively accreting matter or because they are too distant to observe clearly. It's interesting to think about how quiet most of these objects must be. A black hole drifting alone through interstellar space would be almost impossible to detect. It would pass through the galaxy silently, influencing only the occasional grain of dust or stray particle of gas. Sometimes, however, stellar mass black holes reveal themselves in another way, through gravitational waves. When two black holes orbit each other in a binary system, they gradually lose energy by emitting ripples in space-time itself. These ripples, predicted by Einstein's theory of general relativity, travel outward at the speed of light, stretching and compressing space by tiny amounts. In 2015, scientists made the first direct detection of gravitational waves using the LIGO observatories. The signal came from the merger of two stellar mass black holes more than 1 billion light-years away. For a brief moment, the energy released in gravitational waves exceeded the total energy output of all the stars in the observable universe combined, though by the time the waves reached Earth the effect was extraordinarily subtle, changing distances by less than the width of a proton. That detection opened a new way of observing the universe, one that doesn't rely on light at all. Since then, many more black hole mergers have been observed, revealing populations of stellar mass black holes that would otherwise remain hidden. Another intriguing aspect of stellar mass black holes is how diverse they can be. Not all massive stars are identical, and the details of a star's mass, composition, rotation, and environment all influence the black hole that forms. Some black holes spin rapidly, dragging space-time around them in a phenomenon known as frame dragging. Others may rotate more slowly. The spin affects how matter behaves near the event horizon, shaping the structure of accretion disks and the powerful jets that some black holes produce. Those jets are among the most dramatic features associated with black holes. In certain systems, magnetic fields in the accretion disk can channel some of the infalling material into narrow beams that shoot outward at nearly the speed of light, extending for vast distances into space. These jets can influence the surrounding interstellar medium, compressing gas clouds and sometimes even triggering the formation of new stars. So even relatively small black holes can have effects far beyond their immediate surroundings. It's also worth considering how many stellar mass black holes may exist in our own galaxy. The Milky Way contains hundreds of billions of stars, and a significant fraction of those stars are massive enough to end their lives in core collapse supernovae. Not all of those collapses produce black holes, but many do. Estimates suggest that the Milky Way may contain tens of millions of stellar mass black holes. Most of them are invisible, wandering through the galaxy in darkness, relics of stars that lived and died long before the sun was born. Every once in a while, astronomers detect one passing in front of a distant star, producing a phenomenon called gravitational microlensing. The black hole's gravity bends the light from the background star, causing it to brighten temporarily. By carefully analysing these events, scientists can infer the presence of objects that emit no light at all. There is something quietly profound about this. Entire populations of objects, completely invisible, revealed only through the bending of starlight or the faint whisper of gravitational waves. Stellar mass black holes also help astronomers understand the lives of stars. By studying the masses and spins of black holes detected through gravitational waves, scientists can learn about the stars that formed them, the environments in which those stars lived, and the processes that led to their collapse. For example, some black holes detected in mergers have been unexpectedly massive, suggesting that they formed from stars in regions with very low concentrations of heavy elements. In such environments, stars lose less mass through stellar winds, allowing them to retain more material until the moment of collapse. In this way, black holes become records of cosmic history, preserving information about conditions in distant galaxies and earlier eras of the universe. Another gentle reminder emerges here as well. Despite their dramatic reputation, stellar mass black holes are not dangerous unless you are very close to one. The nearest known black hole is thousands of light years away, and even if one were closer, space is so vast that encounters are extraordinarily unlikely. Gravity weakens rapidly with distance, and beyond a certain range, a black hole's influence is no different from that of any other object with the same mass. The idea of black holes roaming the galaxy, swallowing stars at random, belongs more to fiction than to astrophysics. Most of the time, the universe is a quiet place, and stellar mass black holes are part of that quietness. For a long time, astronomers found themselves in an odd situation. On one hand, there was strong evidence for stellar mass black holes, the remnants of massive stars weighing a few times to a few dozen times the mass of the Sun. On the other hand, there were the giants, the supermassive black holes lurking in the centres of galaxies, containing millions or even billions of solar masses. These enormous objects were clearly real, their presence revealed by the motion of stars and the glow of matter falling inward. But between those two extremes there seemed to be a gap. It was as if nature had created small black holes and enormous ones, but nothing in between. and that raised a quiet but persistent question. How do you grow something as large as a supermassive black hole without passing through intermediate stages? If black holes can gain mass by merging or by feeding on gas, then surely there must be objects in the middle range, heavier than stellar remnants but far smaller than galactic giants. Astronomers began referring to these hypothetical objects as intermediate mass black holes. The name itself is simple and descriptive. These would be black holes with masses somewhere between roughly 100 and 100,000 times the mass of the Sun. Not tiny, not enormous, but occupying that long-missing middle ground. For decades, they remained elusive. Part of the difficulty lay in how black holes are detected in the first place. Stellar mass black holes often reveal themselves in binary systems, where they pull matter from companion stars and emit X-rays. Supermassive black holes reveal themselves through the motion of stars in galactic centers, or through the intense radiation of quasars. Intermediate mass black holes, however, fall into an observational grey area. They are often too large to form in typical binary systems, and too small to dominate the centres of large galaxies in obvious ways. So astronomers had to look carefully, patiently, and sometimes creatively. One of the first places scientists began searching was in globular clusters. These are dense, spherical collections of stars, often containing hundreds of thousands of stars packed into a region only a few dozen light-years across. Globular clusters are ancient structures, some nearly as old as the universe itself, and their dense environments make them interesting laboratories for gravitational interactions. In such crowded conditions, stars can interact frequently, sometimes colliding or forming tight binary systems. Over time, these interactions can lead to the gradual sinking of heavier objects toward the center of the cluster, a process known as mass segregation. If stellar mass black holes form in large numbers within a cluster, they might slowly merge, building a larger black hole at the center. That idea is appealing in its simplicity. Many small remnants, gently nudged together by gravity over millions of years, gradually forming something larger. Observational evidence began to hint that this might really be happening. In some globular clusters, astronomers noticed stars moving in ways that suggested the presence of an unseen mass in the center, heavier than a single stellar mass black hole, but far lighter than a supermassive one. Still, the evidence was subtle, and alternative explanations were often possible. Dense clusters of neutron stars or smaller black holes could sometimes mimic the same gravitational effects. The universe rarely gives up its secrets easily, and intermediate mass black holes remained, for many years, strong suspect but not fully confirmed residents of the cosmos. Another place astronomers looked was in small galaxies, particularly dwarf galaxies. These galaxies are far less massive than giants like the Milky Way, and if supermassive black holes exist in large galaxies, it seemed reasonable to wonder whether smaller galaxies might host smaller central black holes. In some cases, observations revealed faint but persistent emissions from galactic centers, suggesting the presence of black holes of intermediate size. These detections were important because they hinted at a possible pathway for growth. Perhaps supermassive black holes began as intermediate ones in the early universe, gradually growing larger through mergers and accretion. Then, in recent years, gravitational wave astronomy began to provide new clues. When LIGO and Virgo detected gravitational waves from merging black holes, some of the masses involved were larger than expected for ordinary stellar remnants. In a few cases, the merged objects appeared to fall into the intermediate mass range, offering some of the clearest evidence yet that such black holes exist. It was a quiet but significant milestone. Objects that had once been hypothetical were beginning to reveal themselves through the ripples they sent across space-time. There is something especially satisfying about discoveries like this. They remind us that the universe is often continuous rather than divided into neat categories. The apparent gap between stellar and supermassive black holes was not a true absence, but simply a region that had been harder to observe. And yet, the question of how intermediate mass black holes form remains an active area of research. One possibility, as mentioned earlier, is repeated mergers in dense star clusters. Another idea involves the direct collapse of very massive stars in the early universe. In the first few 100 million years after the Big Bang, conditions were different from today. The first generations of stars, sometimes called population 3 stars, may have been far more massive than most stars that form now, containing hundreds of times the mass of the Sun. If such stars existed, their collapse could have produced black holes already in the intermediate mass range, providing seeds for the later growth of supermassive black holes. There is also the possibility that large clouds of gas, under certain conditions, might collapse directly into black holes without first forming stars at all. These scenarios are still being studied, but they offer intriguing pathways for the creation of black holes that are neither small nor enormous, but somewhere in between. Another interesting aspect of intermediate mass black holes is how they influence their surroundings. While not as dominant as supermassive black holes, they can still shape the motion of nearby stars and gas. In dense clusters, a central intermediate mass black hole could subtly alter the orbits of stars, creating patterns that careful observation can reveal. These effects are gentle compared to the dramatic jets and luminous accretion disks associated with quasars, but they are no less important scientifically. Sometimes the quietest clues are the most reliable. It's also worth reflecting on how our understanding of black holes has evolved over time. Not long ago, even stellar mass black holes were considered speculative. Then they became accepted, then routinely observed. Now, intermediate mass black holes are following a similar path, moving from hypothesis to evidence to growing certainty. Science often progresses in this gradual way, step by step, with each new observation refining our picture of the universe. And there is something calming about that process. The universe is vast and complex, but it is also patient. Its patterns unfold slowly, giving us time to notice them, to question, to test, and eventually to understand. Intermediate mass black holes also play an important role in helping astronomers understand the growth of galaxies. If supermassive black holes formed by merging smaller ones, then intermediate mass black holes would be natural stepping stones in that process. By studying them, scientists can piece together the history of how the largest structures in the universe evolved. Imagine for a moment a young galaxy billions of years ago. Within it, clusters of stars form, live, and die. Black holes appear, drift, and occasionally merge. Over time, these mergers build larger and larger objects, gradually forming the massive black hole at the galaxy's centre. It's a slow process, unfolding over hundreds of millions of years, far beyond any human timescale, yet governed by the same simple force of gravity that pulls a falling leaf to the ground. There is a kind of quiet continuity in that thought, the same laws, the same processes, working across scales that differ by factors of billions. Another intriguing possibility is that intermediate mass black holes may wander. In some cases, gravitational interactions or galaxy mergers could eject them from their birthplaces, sending them drifting through interstellar or even intergalactic space. These wandering black holes would be almost impossible to detect unless they passed in front of a distant star or encountered a cloud of gas. The universe may contain many such silent travellers moving through darkness, their presence betrayed only by subtle gravitational effects. As observational techniques improve, astronomers are becoming better at finding these elusive objects. New telescopes, both on Earth and in space, are capable of measuring stellar motions with extraordinary precision. Future gravitational wave detectors will be able to observe mergers involving intermediate mass black holes more frequently, providing a clearer picture of their population and distribution. Each new detection helps fill in the missing pieces of the story, and perhaps that is the most comforting way to think about these objects. They are not anomalies or exceptions, but part of a continuum, part of the natural range of outcomes produced by gravity acting over long periods of time. From the collapse of a single massive star to the formation of black holes weighing thousands or millions of suns, the same fundamental principles apply. Intermediate mass black holes are simply one step along that scale, a bridge between the familiar and the extraordinary. If stellar mass black holes are the quiet remnants of individual stars, and intermediate ones are the rare bridges between scales, then the next step in size feels almost difficult to grasp at first. Because at the centres of most galaxies, including our own, reside black holes so large that comparing them to stellar remnants is like comparing a mountain to a grain of sand. These are the supermassive black holes, the giants of the black hole family, containing millions or even billions of times the mass of the Sun. They are not scattered randomly through space, but are found, almost without exception, at the hearts of galaxies, sitting in the deepest regions of the gravitational wells that hold those galaxies together. For a long time, their existence was suspected but uncertain. Astronomers noticed that stars near the centres of galaxies were moving far faster than expected, as if something enormous and invisible were pulling on them. The motions were too rapid to be explained by the combined gravity of stars alone. Something more compact and far more massive had to be there. One of the clearest examples comes from the centre of our own galaxy, the Milky Way. For decades, astronomers carefully tracked the orbits of individual stars near a small, seemingly empty patch of sky in the constellation Sagittarius. These stars moved in tight, fast orbits, some completing a full revolution in just a few years. By applying the laws of gravity, scientists were able to calculate the mass of the object they were orbiting. The result was remarkable. The central object contained about 4 million times the mass of the Sun, compressed into a region smaller than our solar system. No known cluster of stars could remain stable at such density. The only plausible explanation was a supermassive black hole, now known as Sagittarius A star. What makes this discovery especially striking is how calm that region appears most of the time. Despite containing millions of solar masses, Sagittarius A star is relatively quiet compared to the brilliant centres of some other galaxies. Only small amounts of gas fall inward, producing faint emissions that can be detected by radio and infrared telescopes. For the most part, it sits quietly, exerting its influence through gravity alone. This calmness is an important reminder that black holes are not always dramatic. Much of the time, even the largest ones simply exist, shaping the motion of stars over thousands or millions of years without producing spectacular displays. But not all supermassive black holes are so subdued. In some galaxies, enormous amounts of gas and dust fall toward the central black hole, forming vast accretion disks that shine with extraordinary brightness. These objects, known as quasars, can outshine entire galaxies, their light visible across billions of light-years. For a time in the early universe, quasars were among the brightest objects in existence, powered by matter spiralling into supermassive black holes at astonishing rates. It's interesting to consider how efficient this process is. Nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. Accretion onto a black hole can convert 10% or more of the mass of infalling material into energy, making it one of the most efficient energy-producing processes known. And yet, even in these luminous systems, the black hole itself remains dark. The brilliance comes from the material around it, heated by friction and compressed by gravity as it spirals inward. The existence of supermassive black holes raises an intriguing question. How did they become so large? A single star, no matter how massive, cannot produce a black hole of millions of solar masses. The formation of these giants must involve long periods of growth. One pathway is accretion, the gradual accumulation of gas and dust over millions or billions of years. Another pathway is mergers. When galaxies collide and merge, their central black holes can eventually find each other and combine, forming a larger black hole. These mergers are among the most energetic events in the universe, releasing enormous amounts of energy in gravitational waves, Although such events are difficult to detect directly at the supermassive scale with current instruments, astronomers have observed smaller black hole mergers and are developing new detectors capable of sensing the low-frequency gravitational waves produced by merging supermassive black holes. Another mystery lies in the early universe. Observations have revealed quasars that existed less than 1 billion years after the Big Bang, already containing black holes with masses of 1 billion suns or more. Growing such enormous objects in such a short time is challenging to explain, and scientists are still exploring how it could happen. One possibility is that the seeds of these giants were already large, perhaps intermediate mass black holes formed from the collapse of massive gas clouds in the early universe. Another idea is that accretion in the dense environments of early galaxies was far more efficient than it is today, allowing black holes to grow rapidly. Whatever the explanation, the presence of supermassive black holes appears to be closely linked with the formation of galaxies themselves. Observations show a remarkable correlation between the mass of a galaxy's central black hole and the properties of the galaxy's bulge of stars. It's as if the growth of the black hole and the growth of the galaxy are connected, each influencing the other over billions of years. This connection may arise because supermassive black holes can regulate star formation. When large amounts of matter fall into a black hole, some of the energy released can drive powerful winds or jets that heat or expel gas from the galaxy. Without cool gas, new stars cannot form, slowing the growth of the galaxy. In this way, the black hole acts not only as a gravitational anchor, but also as a kind of thermostat, influencing the evolution of its entire host galaxy. The jets produced by some supermassive black holes are among the largest structures in the universe. Narrow beams of particles accelerated to nearly the speed of light can extend for hundreds of thousands of light years, far beyond the visible boundaries of the galaxy itself. These jets interact with the intergalactic medium, shaping enormous bubbles of hot gas. Despite their immense power, these processes unfold slowly on human timescales. A galaxy evolves over billions of years, and the influence of its central black hole is usually subtle, shaping the motion of stars and the distribution of gas rather than producing sudden, dramatic changes. It's also worth reflecting on how small a supermassive black hole is compared to the galaxy it inhabits. Even a black hole with millions of solar masses occupies a region far smaller than the galaxy itself. The Milky Way spans about 100,000 light-years, while the event horizon of Sagittarius A star is only about 24 million kilometers across, smaller than the orbit of Mercury. This contrast between enormous mass and compact size is one of the defining features of black holes. They are both immense and tiny at the same time, containing vast amounts of matter within surprisingly small regions of space. In recent years, astronomers achieved something once thought impossible, directly imaging the shadow of a supermassive black hole. Using a network of radio telescopes spread across the Earth, known as the Event Horizon Telescope, scientists observed the black hole at the center of the galaxy M87, and later Sagittarius A star itself. The images show a bright ring of glowing gas surrounding a dark center, the shadow cast by the event horizon. These images are not photographs in the ordinary sense, but reconstructions based on enormous amounts of data. Still, they provide a powerful confirmation of theories developed over decades, allowing us to see, in a sense, the silhouette of one of these giants. There is something quietly profound about that achievement. For centuries, black holes were purely theoretical. Then they became indirect observations, inferred from the motion of stars and gas. And now, in a way, we can see their outlines against the light of the universe itself. Supermassive black holes also remind us of the vast range of scales in the cosmos, from stellar remnants a few kilometers across to giants, billions of times more massive than the Sun. The same fundamental physics applies. Gravity, simple in its description, produces an extraordinary diversity of structures when given enough time and matter to work with, and time, in the environment near a supermassive black hole, behaves in ways that are both subtle and dramatic. Clocks closer to the event horizon tick more slowly relative to distant observers. Light climbing out of the gravitational well loses energy, shifting toward longer wavelengths. Space itself curves so strongly that paths of light bend into loops, allowing photons to orbit the black hole in unstable rings. These effects are not merely theoretical. They are measured, calculated, and observed, confirming once again that even the most extreme objects in the universe follow consistent laws. When astronomers first began to measure the masses of supermassive black holes, the numbers alone were already difficult to grasp. Millions of suns compressed into a region smaller than a planetary orbit is not something the human mind easily visualizes. Yet as telescopes improved and observations reached farther into the universe, an unexpected realization began to emerge. Some black holes were far larger than even the term supermassive seemed to imply. These objects are often called ultramassive black holes. The name is not formally defined by a strict boundary, but it is generally used for black holes with masses exceeding 10 billion times that of the Sun. At that scale, the differences are not just numerical. They begin to challenge our understanding of how black holes grow and how galaxies evolve around them. To get a sense of scale, it helps to compare familiar points along the spectrum. A stellar mass black hole might contain 10 suns. The black hole at the centre of the Milky Way contains about 4 million. An ultramassive black hole can contain tens of billions. Each step upward represents an enormous increase, not just in mass but in influence over the surrounding cosmos. One of the most well-known examples lies in a distant quasar known as TON 618. Measurements suggest that its central black hole may have a mass exceeding 60 billion suns. Numbers like that are almost impossible to picture directly, but one way to think about it is in terms of the event horizon. A black hole of that size would have a diameter larger than the orbit of Pluto. The entire solar system could fit comfortably inside it, with plenty of room to spare. And yet, despite that immense size, it would still appear small compared to the galaxy around it, just as other black holes do. The contrast between compactness and mass remains one of the defining features of these objects, no matter how large they become. Ultramassive black holes are usually found in very large galaxies, especially giant elliptical galaxies that formed through multiple mergers over billions of years. When galaxies collide, their central black holes eventually drift toward the center of the newly formed galaxy and merge. Over time, repeated mergers can build black holes of extraordinary mass. But mergers alone may not explain everything. There is a practical limit to how quickly black holes can grow by accreting gas. As matter falls inward and heats up, it produces radiation that pushes outward, counteracting further infall. This balance, known as the Eddington limit, sets a kind of natural speed limit on black hole growth. And yet, the existence of ultramassive black holes suggests that, at least in some cases, growth proceeded efficiently for very long periods, or under conditions that allowed the usual limits to be exceeded. Perhaps dense flows of gas fed them continuously. Perhaps early seeds were already large. These questions are still being studied, and each new observation adds another piece to the puzzle. There is also evidence that ultramassive black holes can influence their host galaxies in profound ways. The energy released by matter falling into such a black hole can heat vast regions of interstellar and even intergalactic gas, preventing it from cooling and forming new stars. In this way, the black hole may help determine how quickly its galaxy grows, shaping the evolution of billions of stars over billions of years. It's an interesting reversal of perspective. At first glance, a galaxy seems to be the dominant structure, containing hundreds of billions of stars, while the black hole at its centre occupies only a tiny region. But over long timescales, the black hole can regulate the galaxy's behaviour, influencing the very environment from which stars form. Observing ultramassive black holes is not easy. Most are extremely distant, residing in galaxies billions of light-years away. Astronomers often detect them indirectly by measuring the brightness of quasars or by studying the motion of stars near galactic centres. In some cases, careful observations of gas clouds and stellar velocities reveal the presence of a central mass so large that no other explanation fits. The brightness of quasars powered by ultramassive black holes can be astonishing. These objects shine with the energy of trillions of suns, visible across much of the observable universe. And yet, the light does not come from the black hole itself, but from the swirling disk of matter around it, heated to extraordinary temperatures as gravity pulls it inward. If you could observe such a region up close, the view would be unlike anything familiar. The accretion disk would glow intensely, its inner regions orbiting at significant fractions of the speed of light. Magnetic fields would twist and stretch, channeling some of the inflowing material into jets that shoot outward in opposite directions, sometimes extending for hundreds of thousands of light years. These jets can carry enormous amounts of energy into intergalactic space, inflating bubbles of hot gas larger than entire galaxies. Over time, this activity can change the temperature and structure of the gas surrounding the galaxy, affecting the formation of future generations of stars. Despite all this activity, the black hole itself remains hidden behind the event horizon, silent and invisible, its presence known only through its effects on the world around it. Another fascinating aspect of ultramassive black holes is their rarity. While stellar mass black holes may number in the millions within a single galaxy, ultramassive ones are few and far between. They appear to form only under special conditions, often in the largest galaxies in the densest regions of the universe. These galaxies are sometimes found at the centres of galaxy clusters, enormous structures containing hundreds or even thousands of galaxies bound together by gravity. In such crowded environments, mergers are more common, and the supply of gas can be abundant, providing the ingredients for continued growth. It's possible that some ultramassive black holes reach their enormous sizes relatively early in cosmic history. Observations of distant quasars suggest that very massive black holes already existed when the universe was less than 1 billion years old. That leaves a limited amount of time for them to form and grow, adding another layer of mystery to their origin. Some astronomers suspect that the seeds of these giants may have formed through the direct collapse of massive clouds of gas in the early universe, bypassing the stage of forming ordinary stars. Such direct collapse black holes could begin their lives already containing tens of thousands or hundreds of thousands of solar masses, providing a head start on the path toward becoming ultramassive. Others suggest that dense clusters of stars in early galaxies may have merged repeatedly, building larger and larger black holes through successive collisions. Both scenarios are plausible, and both may occur under different conditions. As observational technology improves, scientists hope to detect gravitational waves from mergers involving intermediate and supermassive black holes. Future space-based detectors, such as the planned laser interferometer space antenna, are expected to be sensitive to the low-frequency waves produced by such events. These observations could reveal how often large black holes merge and how rapidly they grow. There is something quietly remarkable about the idea that ripples in space-time travelling for billions of years can carry information about events involving objects tens of billions of times the mass of the Sun. The universe communicates in subtle ways, and with the right instruments, we can listen. Ultramassive black holes also offer a reminder of how much remains unknown. The physics near the event horizon of such enormous objects is still an active area of research. Questions about how accretion disks behave, how jets are launched, and how energy is transferred to the surrounding environment are still being explored through simulations and observations. Even the largest black holes are not eternal in a strict sense. According to theoretical predictions, all black holes slowly lose mass through Hawking radiation. However, for ultramassive black holes, the timescales involved are almost unimaginable, far longer than the current age of the universe. For all practical purposes, they will remain as they are for trillions upon trillions of years. It's also worth reflecting on how these giants fit into the broader story of cosmic evolution. The universe began in a hot, dense state nearly 14 billion years ago. Over time, matter cooled and gathered into stars, galaxies, and clusters. Black holes formed and grew, becoming part of the structure of galaxies themselves. Ultramassive black holes represent one of the endpoints of that process, objects shaped by billions of years of gravitational interactions, mergers, and accretion. They are not separate from the universe's history, but products of it, shaped by the same physical laws that govern everything else. Long before the first stars ignited, before galaxies gathered into their graceful spirals and glowing clusters, the universe was a very different place. It was hotter, denser, and far more uniform than the cosmos we see today. There were no planets, no suns, no glowing nebulae drifting across the dark. There was only a vast, expanding sea of energy and particles, gradually cooling as space itself stretched outward. And yet, even in those earliest moments, gravity was already at work. Gravity does not need stars or galaxies to exist. It acts wherever mass and energy are present, and in the young universe, matter was spread almost evenly, but not perfectly so. Tiny variations in density existed, slight regions where matter was just a little more concentrated than elsewhere. These differences were small, almost unimaginably subtle, but over time they became the seeds from which cosmic structures would grow. Most of those denser regions would eventually lead to galaxies and clusters, but some scientists have proposed that under the right conditions, certain fluctuations might have been extreme enough to collapse directly into black holes. If that happened, those black holes would have formed long before the first stars were born. They would be, in a sense, fossils of the very early universe. These hypothetical objects are known as primordial black holes. The idea was first seriously explored in the late 20th century, when physicists began considering what might happen if regions of the early universe became dense enough to collapse under their own gravity. Unlike stellar black holes, which form from dying stars, primordial black holes would have formed directly from the raw material of the cosmos itself, from dense pockets of matter and radiation compressed by the conditions of the early universe. What makes this possibility so intriguing is the range of sizes these black holes might have had. Because the density and scale of fluctuations varied, primordial black holes could, in theory, have formed with masses ranging from tiny fractions of a gram to many times the mass of the Sun. Some might have been microscopic, smaller than an atom, while others could rival stellar mass black holes. It's an unusual thought that black holes could exist on such dramatically different scales, some so small that they would evaporate almost instantly through Hawking radiation, others large enough to persist for billions of years. To understand why small primordial black holes would not last long, it helps to return to the idea of Hawking radiation. According to quantum theory, black holes are not completely black. Tiny fluctuations near the event horizon allow them to emit radiation, slowly losing mass over time. The smaller the black hole, the faster this evaporation occurs. A black hole with the mass of a mountain, for example, would evaporate in far less than the current age of the universe. One with the mass of a large asteroid might still exist today, but it would be slowly shrinking, radiating energy so faint that detecting it would be extraordinarily difficult. And that leads to one of the great mysteries surrounding primordial black holes. Do any of them still exist? So far, none have been conclusively confirmed, but scientists continue searching, because primordial black holes could help answer several deep questions about the universe. One of those questions involves dark matter, the invisible substance that makes up most of the mass in galaxies. Dark matter does not emit or absorb light, and its nature remains unknown. Some researchers have proposed that at least part of dark matter could consist of primordial black holes, scattered throughout galaxies, exerting gravitational influence without producing any visible radiation. This idea is appealing in its simplicity. Black holes interact gravitationally, and gravity is exactly how we detect dark matter through its effects on the motion of stars and galaxies. If large numbers of primordial black holes formed in the early universe, they might still be present today, quietly contributing to the unseen mass that shapes cosmic structures. Testing this idea is challenging. Astronomers look for gravitational microlensing events, where a compact object passes in front of a distant star and briefly magnifies its light. Surveys of millions of stars have placed limits on how many black holes of certain masses could exist, ruling out some possibilities but leaving others open. Another possible way to detect primordial black holes involves gravitational waves. If some of the black hole mergers detected by observatories like LIGO involved primordial black holes rather than stellar remnants, their masses and distributions might carry subtle signatures of that origin. This remains an active area of research, with scientists carefully analysing data to see whether any mergers show patterns consistent with primordial formation. There is also the possibility that very small primordial black holes, nearing the end of their evaporation, might produce brief bursts of high-energy radiation. Astronomers have searched for such signals, but so far none have been definitively identified. Still, the absence of evidence is not evidence of absence. The universe is vast, and many phenomena are rare or difficult to detect. It's entirely possible that primordial black holes exist but remain hidden from our instruments, waiting for future telescopes and detectors to reveal them. Another reason primordial black holes are so fascinating is that they offer a potential window into the earliest moments of the universe. Conditions during the first fractions of a second after the Big Bang are difficult to study directly, but if black holes formed during that time, their properties might carry information about those extreme conditions. In this way, primordial black holes would be more than just exotic objects. They would be records of the universe's infancy, preserving clues about the density fluctuations, expansion rates, and physical laws that governed the cosmos when it was less than a second old. It's a remarkable thought, that something as silent and dark as a black hole could serve as a messenger from the earliest epochs of time. There is also a certain quiet beauty in the idea that black holes could form in so many different ways. Some are born from dying stars, others from mergers, and perhaps some from the raw energy of the newborn universe itself. Gravity, it seems, is endlessly creative when given enough time and matter to work with. Primordial black holes, if they exist, would be scattered throughout space, not necessarily bound to galaxies or stars. Some might drift through intergalactic space, solitary and ancient, older than any galaxy we see today. Others might orbit within galaxies, indistinguishable from black holes formed in more recent times except for subtle differences in mass or distribution. And because they could span such a wide range of sizes, primordial black holes challenge our intuition about what a black hole is supposed to be. We often imagine them as massive stellar remnants or galactic giants. But in principle, a black hole can exist at almost any scale, provided enough mass is compressed within a small enough region. That realization broadens the picture of the universe in a gentle but profound way. Black holes are not a single kind of object, but a family, shaped by different origins and environments. Another intriguing possibility involves the role primordial black holes might have played in cosmic evolution. Some researchers have suggested that they could have acted as seeds for the formation of galaxies, providing gravitational centers around which matter could gather. If even a small number of primordial black holes formed with substantial masses, they might have accelerated the growth of the first galaxies and supermassive black holes. This idea remains speculative, but it highlights how interconnected cosmic processes can be. Events in the first seconds of the universe might still influence structures billions of years later. There is also something quietly humbling about contemplating these objects. Primordial black holes, if they exist, would have formed long before the Sun, long before Earth, long before any life emerged to wonder about them. They would have existed through the entire history of the universe as we know it, silent witnesses to the formation of galaxies, the birth and death of stars, and the slow unfolding of cosmic time. And yet, despite their ancient origins, they remain elusive, like shadows at the edge of our understanding. As observational techniques continue to improve, astronomers hope to learn more about the early universe through new measurements of the cosmic microwave background, gravitational waves, and deep surveys of distant galaxies. Each new dataset provides another opportunity to test the idea of primordial black holes, to look for subtle signatures that might reveal their presence. Perhaps one day clear evidence will emerge, and primordial black holes will move from hypothesis to established reality, joining stellar and supermassive black holes as familiar members of the cosmic landscape. For now, they remain possibilities, intriguing and mysterious, reminders that the universe still holds many secrets waiting to be uncovered. Not all black holes, at least in theory, need to be enormous. After spending time with objects weighing millions or billions of suns, it may feel strange to shift attention toward the opposite extreme, toward black holes so small that they would be invisible not just across galaxies, but even at distances measured in meters. Yet physics allows for that possibility, and the idea of micro-black holes has intrigued scientists for decades. A micro-black hole, sometimes called a quantum black hole or miniature black hole, would be a black hole with a mass far smaller than any formed from stars. Instead of weighing several times the mass of the Sun, it might weigh as much as a mountain, or a large asteroid, or in some theoretical cases far less. Its event horizon would be extraordinarily tiny, far smaller than an atom in many scenarios, making it impossible to observe directly with conventional instruments. To understand how such an object could exist, it helps to remember a simple principle. A black hole forms whenever enough mass or energy is compressed into a sufficiently small region. There is no rule saying that region must be large. The same equations that describe stellar black holes also allow solutions at much smaller scales, provided the necessary density is reached. In the early universe, as we discussed earlier, extremely dense conditions might have allowed small black holes to form naturally. But there is another possibility that scientists have considered, one that brings the idea of micro-black holes closer to modern experiments. At very high energies, such as those produced in powerful particle accelerators or in cosmic ray collisions in Earth's atmosphere, particles can collide with enormous concentration of energy in extremely tiny volumes. In principle, if the energy density in such a collision became high enough, it could briefly create a microscopic black hole. This idea may sound like science fiction, but it arises naturally from certain theories of physics, especially those involving extraspatial dimensions. Some models suggest that gravity may become much stronger at very small scales if additional dimensions of space exist beyond the three we experience. In such scenarios, the energy required to create a micro-black hole might be lower than previously thought, perhaps within reach of high-energy experiments. When the Large Hadron Collider began operating, there was public curiosity and sometimes concern about whether microscopic black holes might be produced. Physicists carefully studied the question and concluded that even if such black holes formed, they would be completely harmless. In fact, they would evaporate almost instantly through Hawking radiation, disappearing in fractions of a second. That evaporation process is one of the most fascinating aspects of micro-black holes. Unlike massive black holes, which lose mass extremely slowly, very small black holes radiate energy rapidly. The smaller the black hole, the higher its temperature and the faster it evaporates. A microscopic black hole could vanish almost as soon as it formed, releasing a tiny burst of particles and radiation. This fleeting existence is why some scientists describe them as objects that might flicker in and out of existence, appearing for an instant before dissolving back into energy. There is something almost poetic about that idea, though the physics behind it is precise and mathematical. A region of space briefly collapses into a black hole, exists for a moment shorter than a blink, and then evaporates completely, leaving only a faint signature of particles spreading outward. Detecting such events would be extraordinarily challenging. The signals would be subtle and easily masked by other processes occurring in high-energy collisions. So far, no confirmed evidence of micro-black holes has been observed in laboratory experiments, but the search continues, both in particle accelerators and in observations of cosmic rays. Another intriguing possibility is that high-energy events in the universe, such as collisions between extremely energetic particles or the environments near neutron stars and black holes, might occasionally produce tiny black holes naturally. If so, they would form and evaporate so quickly that only their radiation would remain, making them difficult to distinguish from other energetic phenomena. Micro-black holes are also interesting because they sit at the intersection of two major areas of physics: general relativity and quantum mechanics. Large black holes are described very well by general relativity, while the behavior of extremely small objects is governed by quantum theory. Micro-black holes would exist in a regime where both sets of laws are equally important, offering a possible window into the long-sought theory of quantum gravity. Physicists hope that understanding such objects, even theoretically, could help answer deep questions about the nature of space, time, and information. What happens to information that falls into a black hole? How does gravity behave at the smallest scales? Are space and time continuous, or do they have a fundamental graininess at extremely tiny distances? These are not easy questions, and they do not have simple answers yet. But micro-black holes provide a kind of conceptual laboratory where such ideas can be explored. There is also an interesting contrast between micro-black holes and their larger relatives. When we think of black holes, we often imagine them as eternal, or nearly so, objects that persist for billions or trillions of years. Micro-black holes, if they exist, would be the opposite: brief, transient, lasting less than a fraction of a second. They would be the shortest-lived black holes imaginable. And yet, during that fleeting existence, they would still possess the defining features of black holes: an event horizon, a temperature, a gravitational field. Even for an instant, they would be genuine members of the black hole family. It's worth pausing to appreciate how flexible the concept of the black hole really is. From ultramassive giants larger than planetary systems to hypothetical objects smaller than atoms, the same underlying principles apply. Gravity, energy, and the geometry of space-time shape objects across an enormous range of scales. Another reason micro-black holes are so fascinating is that they challenge our intuition about emptiness. We often think of empty space as truly empty, but quantum theory tells us that even a perfect vacuum is filled with fluctuations, tiny, temporary changes in energy that constantly appear and disappear. These fluctuations are normally far too small to produce anything macroscopic, but under extreme conditions they might play a role in the formation or evaporation of tiny black holes. In this sense, micro-black holes remind us that the universe is not only vast but also subtle. Phenomena at the smaller scales can be just as complex and mysterious as those at the larger scales. There is also a calming perspective to be found here. Even the most extreme objects in the universe follow predictable rules. The formation and evaporation of micro-black holes, if it occurs, would be governed by the same physical laws that describe stars, planets, and galaxies. The universe, for all its strangeness, is consistent. Scientists sometimes speculate about whether micro-black holes could have practical implications, perhaps in future technologies or as probes of fundamental physics. For now, these ideas remain far in the realm of theory, but they illustrate how curiosity about the universe often leads to unexpected possibilities. And yet, even without practical applications, the study of such objects has value. It deepens our understanding of the cosmos and of the laws that govern it. It reminds us that reality is often more intricate and surprising than our everyday experiences suggest. If micro-black holes do exist, they would be among the most elusive phenomena in nature, forming and vanishing in the blink of an eye, leaving behind only faint traces of their presence. They would be like sparks in the darkness, brief flashes of extreme gravity that appear and disappear before anyone could ever see them directly. As research continues, physicists and astronomers will keep searching for evidence, refining theories, and designing experiments capable of probing ever smaller scales. Whether micro-black holes are ultimately discovered or remain purely theoretical, The journey of exploring the possibility teaches us something important about the universe and about the way science works, gradually testing ideas and building understanding step by step. Most objects in the universe spin. Planets rotate, stars turn slowly or rapidly depending on their history. Galaxies revolve in vast, graceful motions that take hundreds of millions of years to complete a single turn. Spin is almost unavoidable in nature, because anything that forms from collapsing clouds of gas and dust tends to inherit some slight motion, and as the material contracts, that motion speeds up. It's the same reason an ice skater spins faster when pulling in their arms. Angular momentum is conserved, and the universe follows that rule with quiet consistency, so it should not be surprising that many black holes spin as well. Yet the consequences of that spinning are far more remarkable than one might expect. A rotating black hole, often called a Kerr black hole, after the mathematician Roy Kerr, who first described the solution to Einstein's equations in 1963, does more than simply turn in place. Its rotation changes the structure of space and time around it in ways that are subtle at a distance but extraordinary close in. To begin understanding this, it helps to recall that in general relativity, gravity is not a force in the traditional sense. Instead, mass and energy curve space-time, shaping the paths that objects and light follow. A non-rotating black hole creates a symmetrical curvature, like a perfectly round depression in a flexible surface. But when a black hole rotates, the geometry becomes more complicated. The spinning mass drags space-time along with it, a phenomenon known as frame dragging. Space itself near the black hole is pulled into motion, as if the fabric of the universe were being gently twisted. This effect is not just theoretical. Even Earth produces a tiny amount of frame dragging because it rotates, and this has been measured by extremely precise experiments, such as the Gravity Probe B mission. Around a rotating black hole, however, the effect becomes enormously stronger. Close to such a black hole there exists a region called the ergosphere, a name that might sound technical but describes something quite fascinating. The ergosphere lies just outside the event horizon and has a peculiar property. Within it, space-time is dragged around so strongly that nothing can remain stationary relative to distant space. Everything must move in the direction of the black hole's rotation. It's important to note that this does not mean objects are forced to spiral inward immediately. They can still orbit or even escape, but they cannot remain still. The flow of space-time itself carries them along, like leaves caught in a slow but irresistible current. There is something quietly mesmerizing about that idea. Space is not merely a passive stage on which events unfold. Near a rotating black hole, the stage itself begins to move. The ergosphere also allows for a remarkable theoretical possibility known as the Penrose process, proposed by physicist Roger Penrose. In principle, an object entering the ergosphere could split into two parts, one falling into the black hole and the other escaping with more energy than the original object had. The extra energy would come from the rotational energy of the black hole itself, meaning that, at least in theory, energy can be extracted from a spinning black hole. This is not just an abstract concept. Some astrophysicists believe that processes similar to this may power the enormous jets observed in certain black hole systems, where streams of particles are accelerated to nearly the speed of light and launched far into space. Rotation also changes the structure of the event horizon itself. In a non-rotating black hole, the event horizon is a simple sphere. In a rotating one, the shape is still roughly spherical but flattens slightly at the poles, and the internal geometry becomes far more complex. The singularity inside a rotating black hole is predicted in classical general relativity to take the form of a ring rather than a point. Whether this description holds in a full theory of quantum gravity remains uncertain, but it illustrates how profoundly rotation alters the mathematics of black holes. Another effect of rotation is that the innermost stable orbit around a black hole moves closer to the event horizon as the spin increases. This means that matter in an accretion disk around a rapidly spinning black hole can orbit closer, moving faster and heating to higher temperatures, producing more intense radiation. In this way, the spin of a black hole directly influences the brightness and behavior of the material around it. Two black holes of equal mass but different spins can look very different from a distance, simply because of how their rotation affects the flow of gas and light nearby. Astronomers have developed methods to estimate black hole spin by studying the X-ray emissions from accretion disks and the shape of spectral lines produced by iron atoms in the hot gas. These observations suggest that many black holes, both stellar mass and supermassive, are indeed rotating, sometimes at a significant fraction of the maximum rate allowed by physics. That maximum rate is itself an interesting concept. There is a theoretical limit to how fast a black hole can spin. If it rotated faster than this limit, the event horizon would disappear, exposing the singularity, something known as a naked singularity. Most physicists believe that nature prevents this from happening, a principle sometimes called cosmic censorship, though the exact mechanisms remain an area of study. What determines how fast a black hole spins? The answer lies in its history. A black hole formed from a collapsing star inherits the angular momentum of that star. If it later accretes matter from a disk, the infalling material can spin it up further, much like pushing a merry-go-round repeatedly in the same direction. Mergers also play a role. When two black holes collide and merge, the resulting black hole spin depends on the masses and spins of the original pair, as well as the geometry of their orbits. Gravitational wave observations have begun to reveal clues about these spins, offering insights into how black holes grow and evolve over time. It's fascinating to think that the spin of a black hole is, in a sense, a memory of its past, a record of the motions and interactions that shaped it. Even though the details of the matter that form the black hole are hidden behind the event horizon, properties like mass and spin remain, encoding part of its history. Rotation also has subtle effects on time itself. Close to a rotating black hole, the paths that objects and light can take become more complex, and time dilation interacts with frame dragging in intricate ways. Clocks moving with the rotation may experience time differently from those moving against it, depending on their trajectories. These are not effects anyone is likely to experience firsthand, of course, but they illustrate how rich and varied the physics of black holes can be. Another intriguing aspect of rotating black holes is how they shape the appearance of their surroundings. Light travelling near a spinning black hole follows curved paths influenced not only by gravity but by the dragging of space-time. This can distort the appearance of accretion disks, producing asymmetric patterns in the light we observe. Computer simulations of these effects reveal views that are both beautiful and strange: glowing disks bent into arcs, rings of light formed by photons orbiting the black hole multiple times before escaping, shadows that shift subtly depending on the angle of observation. These images are not merely artistic interpretations, they are grounded in precise calculations based on general relativity, showing how space and time behave in extreme conditions. Rotation may also help explain some of the most energetic phenomena in the universe. In certain systems, magnetic fields anchored in the accretion disk and twisted by the black hole's spin can extract energy and launch powerful jets. These jets can travel vast distances, sometimes extending far beyond the boundaries of the host galaxy. Despite their dramatic appearance, the processes that produce these jets unfold gradually, governed by the steady flow of matter and the persistent twisting of magnetic fields. There is nothing hurried about them on cosmic timescales. They are slow, powerful, and sustained. It's worth pausing to reflect on how remarkable it is that a region of space from which nothing can escape can nevertheless influence its surroundings so profoundly. A rotating black hole can shape the motion of stars, the flow of gas, the structure of magnetic fields, and the evolution of entire galaxies, all while remaining hidden behind its event horizon. And yet, for all their complexity, rotating black holes are still governed by a small set of parameters. According to the no-hair theorem, a black hole can be fully described by its mass, its spin, and its electric charge. Most astrophysical black holes are expected to have negligible charge, leaving mass and spin as the primary characteristics. This simplicity is one of the elegant features of black hole physics. No matter how complicated the processes that formed a black hole, its external description becomes remarkably straightforward. Still, simplicity in description does not mean simplicity in behavior. The interplay between rotation, gravity, and electromagnetic fields produces phenomena that continue to challenge and inspire scientists. As observations improve, astronomers are learning more about how common rapidly spinning black holes are, and how their spins evolve over time. Each new measurement adds another piece to the puzzle, helping us understand not only black holes themselves, but the history of the stars and galaxies that created them. There is also a broader perspective to consider. Rotation is a universal feature, appearing at every scale. From the spin of electrons to the rotation of galaxies, rotating black holes are in a sense part of that continuum, another example of how motion and gravity shape the universe. Most of the black holes we've been talking about so far are described by just two main properties: mass and spin. In the real universe, those two characteristics explain nearly everything astronomers observe, but the mathematics of general relativity allows for a third possibility, one that is far less familiar and far more difficult to encounter in nature. A black hole, at least in theory, can also carry electric charge. These objects are known as charged black holes, or more formally, Reissner-Nordström black holes when they are not rotating, and Kerr-Newman black holes when they spin as well as carry charge. The names may sound complicated, but the idea behind them is straightforward. Just as an ordinary object can carry electric charge, a black hole could, in principle, form from matter that contains more positive charge than negative, or vice versa. At first, that might seem entirely reasonable. After all, stars are made of charged particles. Protons carry positive charge, electrons carry negative charge, and plasma in stellar interiors is constantly moving and interacting. So why wouldn't a collapsing star sometimes leave behind a black hole with a net electric charge? The answer lies in how powerful electric forces are compared to gravity. Electric forces are vastly stronger than gravitational ones. If a black hole began to accumulate significant charge, it would immediately start attracting particles of the opposite charge from the surrounding environment. Those particles would quickly neutralize the imbalance. Over time, the black hole would return to an almost perfectly neutral state. This is why astronomers expect that most real black holes carry little or no net electric charge. The universe tends to balance charges efficiently, especially over long periods. Even so, the theoretical study of charged black holes has been extremely valuable because it reveals how gravity and electromagnetism interact under extreme conditions. One of the key differences between a charged black hole and an uncharged one is the structure of its event horizon. In the simplest non-rotating, uncharged case, there is a single event horizon, a boundary beyond which nothing can escape. In a charged black hole, the mathematics predicts something more complex: two horizons, an outer event horizon and an inner horizon. The outer horizon behaves much like the one we've already discussed, marking the point of no return. The inner horizon, however, introduces subtleties in the structure of space-time that are still being studied. Between these horizons, the geometry of space and time behaves in unusual ways, and the classical equations suggest the possibility of exotic internal structures. Whether those structures would actually exist in reality is uncertain, because quantum effects are likely to become important in such extreme environments. Still, the theoretical models provide valuable insights into how space-time behaves under conditions far beyond anything we can replicate on Earth. Another interesting property of charged black holes is how electric charge modifies the gravitational field. In a sense, the electric charge partially counteracts the gravitational attraction, altering the shape of space-time around the black hole. This does not mean the black hole becomes less dangerous in any practical sense. but it changes the equations that describe orbits and trajectories near the event horizon. There is also a theoretical limit to how much charge a black hole can have. If the charge were too large relative to the mass, the equations predict that the event horizon would disappear entirely, leaving what is called a naked singularity. Most physicists believe that nature prevents such situations through mechanisms that are not yet fully understood, a principle related to the idea of cosmic censorship. In practice, this means that even if charged black holes could form, their charge would likely remain well below this extreme limit. The study of charged black holes has also played an important role in the development of black hole thermodynamics. When physicists began exploring how black holes behave in quantum theory, charged black holes provided useful models for understanding temperature, entropy, and the emission of radiation. For example, the presence of charge affects the temperature of a black hole as predicted by Hawking radiation. The more charge a black hole has, the lower its temperature becomes, altering the rate at which it would evaporate over time. These theoretical explorations have helped deepen our understanding of how gravity, quantum mechanics, and thermodynamics intersect. There is something quietly fascinating about how ideas that may never occur in nature can still illuminate the laws of physics. Charged black holes might be rare or non-existent in the observable universe, yet studying them helps scientists test theories and explore possibilities that lead to broader insights. It's also worth considering that extreme environments in the universe sometimes produce surprising conditions. Regions near neutron stars and magnetars, for example, can contain extraordinarily strong magnetic fields and energetic plasmas. While it remains unlikely that large net charges could persist long enough to form significantly charged black holes, the universe often finds ways to surprise us, so the possibility cannot be dismissed entirely. Another reason charged black holes capture the imagination is the way they illustrate the unity of physical laws. Gravity and electromagnetism are two of the fundamental interactions in nature, and black holes provide a setting where both can be studied together in regimes far beyond ordinary experience. In theoretical physics, charged black holes also appear in discussions of higher dimensional spacetimes, string theory, and other advanced frameworks that attempt to unify all the fundamental forces. In these contexts, black holes with various charges, not just electric charge but other kinds associated with hypothetical fields, play important roles in exploring how the universe might behave at the deepest levels. From a more reflective perspective, charged black holes remind us that not every possibility predicted by mathematics must be common in nature. Some solutions to the equations of physics describe situations that are unlikely or unstable, yet they remain important because they reveal the full range of what the laws of nature permit. And sometimes, understanding the limits of possibility is just as valuable as understanding what actually occurs. If you imagine drifting near a charged black hole, the experience would differ in subtle ways from what we described earlier. In addition to the familiar pull of gravity and the effects of curved space-time, there would be electric fields influencing charged particles, shaping the motion of plasma and radiation in the surrounding environment. The interplay between these forces would create patterns of motion and emission unlike those near ordinary black holes. Such scenarios remain largely theoretical, but computer simulations allow scientists to explore them, revealing how matter and fields might behave in these exotic conditions. There is also a certain elegance in the mathematical descriptions of charged black holes. The equations become more complex, yet they retain a kind of symmetry and structure that physicists find deeply satisfying. These solutions are like intricate patterns woven into the fabric of general relativity, showing how rich and varied spacetime can be. As our journey continues, it becomes clear that black holes are not defined by a single feature, but by a combination of properties: mass, spin, charge, and the environment around them. Each variation adds another layer to the story, another way in which gravity shapes the universe. Not every black hole spends its existence alone. In many parts of the universe, gravity brings objects together, sometimes gently, sometimes over immense stretches of time. Stars often form in pairs, and galaxies merge with one another in slow, majestic encounters that take hundreds of millions of years to unfold. It should come as no surprise, then, that black holes also sometimes find themselves in pairs, bound together by gravity, orbiting each other in a quiet and patient dance. These systems are known as binary black holes. At first glance, it may be difficult to imagine what such a system would even look like. After all, black holes emit no light. Two of them orbiting each other would be completely invisible to ordinary telescopes. And yet, despite their darkness, their motion can reveal them in remarkable ways, especially when they begin to spiral closer together. To understand how binary black holes form, it helps to return to the lives of stars. Many massive stars exist in binary systems, orbiting a companion from the time they're born. If both stars in such a pair are massive enough, each may eventually collapse into a black hole. The result is a system containing two black holes locked in orbit, continuing the motion that began when they were still shining suns. Another pathway involves dense star clusters. In these crowded environments, gravitational interactions are frequent. Black holes formed from earlier generations of stars can encounter one another, lose energy through interactions with surrounding stars, and eventually form bound pairs. Over time, these pairs tighten their orbits, gradually moving closer together. There is something quietly fascinating about the patience of this process. A binary black hole can orbit for millions or even billions of years, circling one another in darkness, their presence known only through subtle gravitational effects. But the dance does not remain unchanged forever. According to Einstein's theory of general relativity, orbiting massive objects produce gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system. As energy is lost, the orbit shrinks, and the black holes move closer together. The process is extremely slow at first, almost imperceptible, but as the distance decreases, the emission of gravitational waves grows stronger, and the inspiral accelerates. In the final moments before merger, the black holes orbit each other at incredible speeds, sometimes completing dozens of orbits per second. Space itself is shaking with the energy of their motion, and enormous amounts of energy are radiated away in gravitational waves. Then, in a fraction of a second, the two black holes merge into one, settling into a new, slightly larger black hole that continues to ring like a bell, emitting gravitational waves as it stabilizes. This sequence, inspiral, merger, and ring down, is one of the most extraordinary phenomena ever predicted by physics, and in recent years, directly observed. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves from the merger of two stellar mass black holes more than 1 billion light-years away. The signal lasted only a fraction of a second, but it carried unmistakable evidence of two massive objects spiraling together and merging. It was the first direct detection of gravitational waves, a discovery that confirmed a prediction Einstein had made a century earlier and opened an entirely new way of observing the universe. What makes this achievement even more remarkable is how subtle the effect was by the time the waves reached Earth. The passing gravitational waves changed the lengths of LIGO's detectors by less than 1,000th the diameter of a proton. Measuring such a tiny change required extraordinary precision, careful engineering, and years of preparation. Since that first detection, dozens of binary black hole mergers have been observed. Each event provides new information about the masses, spins, and distribution of black holes in the universe. Some of the black holes detected in these mergers are larger than expected, hinting at formation processes that are still being studied. Binary black holes are not limited to stellar mass objects. In the centres of galaxies, supermassive black holes can also form binary systems when galaxies merge. As the galaxy's stars and gas settle into a new structure, the central black holes gradually drift toward one another, eventually forming a bound pair. These supermassive binary systems are expected to emit gravitational waves as well. but at much lower frequencies than those detected by LIGO. Future space-based observatories, such as the planned Laser Interferometer Space Antenna, are designed to detect these slower, deeper ripples, allowing scientists to observe the mergers of giants millions or billions of times the mass of the Sun. There is something quietly poetic about the idea that the universe itself can act like a vast instrument, vibrating in response to the motion of massive objects, and that we have learned to listen to those vibrations. Binary black holes also offer insights into the environments where they form. By studying the masses and spins of merging black holes, astronomers can infer whether they formed together as a binary star system or came together later in a dense cluster. The orientation of their spins and the distribution of their masses carry clues about their history. In this way, each merger becomes not just a dramatic event, but also a message, carrying information about distant regions of space and long-vanished stars. It's also worth reflecting on how long these systems can persist before merging. Two black holes separated by a large distance may take billions of years to spiral together. Many binary black holes that exist today will not merge until far in the future, long after the Sun has expanded into a red giant and Earth, in its present form, is no longer here. Time on these scales becomes almost unimaginable, yet the laws governing the motion remain simple and consistent. Gravity pulls, energy radiates, orbits shrink, and eventually the dance ends in union. The merger itself is not destructive in the way we might imagine from ordinary collisions. Black holes do not crash together like solid objects. Instead, their event horizons merge smoothly, forming a new horizon that settles into a stable shape. The energy released in gravitational waves can be enormous, sometimes equivalent to several solar masses converted directly into energy, but this energy spreads outward through space-time rather than as light or heat. Another interesting aspect of binary black holes is how they can influence their surroundings before merging. If gas is present, the motion of the black holes can stir and heat the material, producing electromagnetic signals that may accompany the gravitational waves. Observing both types of signals together, known as multi-messenger astronomy, allows scientists to study these systems in greater detail. There is also the possibility that some binary black holes never merge at all, at least not within the current age of the universe. If their orbits are wide enough, the emission of gravitational waves may be too weak to bring them together within billions of years. These systems would continue orbiting quietly, unseen, part of the vast population of black holes scattered through galaxies, and that is perhaps one of the most calming perspectives of all. Even the most dramatic cosmic events are rare compared to the long stretches of quiet in between. For every merger that sends ripples across the universe, there are countless binary systems orbiting peacefully in darkness, their slow motion unfolding over timescales far beyond human experience. As two black holes orbit one another over immense stretches of time, their motion is at first almost unchanging, a slow circling in the darkness, silent and patient. But gravity is never entirely still. With each orbit, a tiny amount of energy is carried away in the form of gravitational waves, ripples spreading outward through space-time itself. The loss is incredibly small at the beginning, so small that it takes millions or billions of years to make any noticeable difference. Yet the process never stops. Orbit by orbit, the distance between the two black holes shrinks. Eventually, the pace begins to change. The closer the black holes draw to one another, the faster they move. Faster motion produces stronger gravitational waves, and stronger waves carry away more energy. This creates a quiet but powerful feedback loop. The orbit tightens, the speed increases, and the tightening accelerates further. What began as a slow spiral becomes, in its final moments, a rapid and dramatic inward sweep. It helps to picture this not as a sudden collision, but as a gradual tightening of a cosmic whirl, a dance that begins slowly and ends in a swift, decisive embrace. In the last few seconds, the black holes may be orbiting each other dozens or even hundreds of times per second. Moving at a significant fraction of the speed of light, space itself is trembling with the intensity of their motion, and then, in a moment that lasts less than a heartbeat, the two horizons touch and merge, forming a single, larger black hole. What happens during that instant is one of the most energetic events in the universe. A portion of the total mass of the system, often equivalent to several suns, is converted directly into energy and carried away by gravitational waves. These waves radiate outward in all directions, expanding across the cosmos at the speed of light, stretching and compressing space by tiny amounts as they pass. The newly formed black hole does not immediately settle into perfect stillness. Instead, it undergoes a phase known as ring down. Much like a bell that continues to vibrate after being struck, the merged black hole oscillates briefly, emitting gravitational waves at characteristic frequencies until it reaches a stable shape. Those final vibrations carry a remarkable amount of information. From them, physicists can determine the mass and spin of the new black hole and confirm whether the behaviour matches the predictions of general relativity. So far, every observed merger has agreed with Einstein's theory with astonishing precision. For most of human history, all of this would have been completely unknown. Gravitational waves are extraordinarily faint by the time they reach Earth. Even the merger of black holes billions of times the mass of the Sun produces changes in distance smaller than the width of a proton when detected here, and yet in 2015, scientists succeeded in measuring those changes for the first time. The detectors that made this possible, the LIGO observatories, are marvels of engineering. Each consists of two long tunnels arranged in an L shape, with laser beams travelling back and forth along their lengths. When a gravitational wave passes, it changes the length of one arm slightly more than the other, altering the pattern of a light detected when the beams recombine. The change is unimaginably small, far smaller than any mechanical movement we can feel or see, but with careful isolation from vibrations and noise, the signal becomes detectable. On September 14th, 2015, both LIGO detectors, separated by thousands of kilometres, recorded the same faint rising signal, a chirp lasting only a fraction of a second. That sound, translated into audio frequencies, was the final moments of two black holes merging more than 1 billion light-years away. It was the first direct detection of gravitational waves and the first direct observation of a black hole merger. There is something deeply moving about that achievement. A vibration that began long before humans existed travelled across intergalactic space, passing through countless stars and clouds of gas, and finally reached Earth, where delicate instruments were waiting to listen. Since then, many more mergers have been detected, each one adding to our understanding of how black holes form, evolve, and interact. Some involve black holes of similar masses. Others reveal unexpected combinations, including objects heavier than most stellar remnants, hinting at complex formation histories. These observations have opened a new window on the universe, one that does not rely on light. For centuries, astronomy was limited to what could be seen with telescopes. Then radio waves, X-rays, and other forms of electromagnetic radiation expanded our view. Gravitational waves have now added another sense, allowing us to hear the motions of massive objects in the darkness. It's an interesting thought that the universe has always been filled with these ripples, passing silently through space, unnoticed until recently. Every merging black hole, every neutron-star collision, every massive object in rapid motion contributes to this quiet symphony. Merging black holes are also important for another reason. They play a key role in the growth of larger black holes. When two galaxies collide, their central black holes eventually sink toward the centre of the merged system, forming a binary and ultimately merging. Over billions of years, repeated mergers can build black holes of enormous mass, helping to explain the existence of supermassive and ultramassive black holes. The process is not always straightforward. Before merging, the two black holes must lose enough energy to approach each other closely, In dense galactic centres, interactions with stars and gas can help carry away that energy, gradually shrinking the orbit. In some cases, this stage may take a very long time, and astronomers are still studying how efficiently it occurs. There is also a subtle effect known as gravitational recoil. When two black holes merge, the gravitational waves emitted are not always perfectly symmetrical. If more energy is radiated in one direction than another, the newly formed black hole can receive a small kick, moving away from its original position. In extreme cases, this recoil could even eject a black hole from its host galaxy, sending it drifting through intergalactic space. The idea of a supermassive black hole wandering alone between galaxies is both strange and fascinating, a reminder that even the largest structures in the universe are subject to motion and change. Another aspect of black hole mergers that scientists study carefully is the orientation of the spins. If the spins of the two black holes are aligned with their orbit, the merger proceeds differently than if the spins are tilted or opposed. These details affect the shape of the gravitational wave signal, allowing researchers to reconstruct the geometry of the system long after the event itself has passed. In this way, gravitational waves act almost like fingerprints, each merger leaving a unique pattern that tells a story about its origins. The environments where mergers occur can vary widely. Some binary black holes form from pairs of stars that evolve together, while others may form in dense star clusters, where gravitational encounters bring black holes together that were not originally born as companions. Distinguishing between these scenarios helps astronomers understand the life cycles of stars and the dynamics of clusters. There is also growing interest in the possibility of observing mergers involving intermediate mass black holes, or even supermassive ones. These events produce gravitational waves at lower frequencies, which cannot be detected by ground-based observatories because of vibrations and noise from Earth itself. Future space-based detectors, with arms millions of kilometers long, will be able to measure these slower ripples, revealing mergers of enormous black holes across the universe. It is remarkable how quickly this field has advanced. Only a few decades ago, gravitational waves were still considered extremely difficult to detect. Now they are becoming a routine part of astronomy, providing insights that were once thought impossible. From a more reflective perspective, merging black holes offer a powerful illustration of how dynamic the universe is. Even objects that seem eternal and unchanging are part of a larger story, moving, interacting, and evolving over time. Galaxies collide, stars explode, black holes merge, and new structures form from the debris. Yet all of this unfolds on timescales so vast that, to us, the night sky appears calm and still. If you could watch a pair of black holes over millions of years, you would see their orbits slowly shrinking, their motion gradually quickening until the final spiral happened in an instant. It would be like watching the hands of a clock that moves almost imperceptibly for hours, and then suddenly sweeps forward in a rapid motion. There is also something quietly beautiful in the simplicity of the process. Gravity pulls, energy radiates, orbits decay. The laws are straightforward, yet the consequences are profound. Another thought that often surprises people is how clean these mergers are compared to collisions of ordinary matter. When two stars collide, the interaction is chaotic, producing shock waves, turbulent flows, and complex radiation. When two black holes merge, there is no surface to shatter, no material to scatter. The event horizons simply join, and the energy is carried away smoothly in gravitational waves. It is, in a sense, one of the most elegant forms of collision in the universe. And even after the merger, the story continues. The new black hole may remain in a galaxy where future mergers await, or it may drift through space, interacting with its environment in subtle ways. Over billions of years, it may grow, spin down, or encounter new companions. It becomes clear that mergers are not rare accidents, but an essential part of cosmic evolution. They are the mechanisms by which black holes grow, by which galaxies change, and by which the universe reshapes itself on the grandest scales. Not every black hole remains where it was born. While many stay in binary systems or at the centres of galaxies, some eventually find themselves alone, drifting through space with no star to orbit and no galaxy to anchor them closely. These solitary travellers are often called rogue black holes, and they may be far more common than we once imagined. The idea of a rogue black hole can feel unsettling at first, perhaps because the word rogue suggests something unpredictable or dangerous. But in reality, these objects are simply black holes that have been set adrift by the ordinary workings of gravity over long periods of time. The universe is dynamic. Stars move, clusters interact, galaxies collide, and sometimes those processes send objects on long, solitary journeys. There are several ways a black hole can become a wanderer. One of the most straightforward begins with the death of a massive star in a binary system. Imagine two stars orbiting each other for millions of years. Eventually one of them collapses into a black hole. If the collapse is accompanied by an asymmetric supernova explosion, the newly formed black hole can receive a powerful kick, a sudden burst of momentum caused by uneven ejection of material. That kick may be strong enough to break the gravitational bond between the two objects, sending the black hole drifting away into interstellar space. The companion star continues on its own path, and the black hole becomes a solitary traveller, moving quietly through the galaxy. Another pathway involves gravitational interactions in dense star clusters. In these crowded environments, stars and black holes frequently pass close to one another. Occasionally, a close encounter between several massive objects can fling one of them outward at high speed, a process sometimes called gravitational slingshotting. The ejected object may escape the cluster entirely, beginning a long journey through the galaxy. Over billions of years, such processes can populate galaxies with countless isolated black holes, most of them invisible and almost impossible to detect directly. There is also a more dramatic mechanism that can produce rogue black holes, involving mergers of supermassive black holes at the centres of galaxies. As we discussed earlier, when two black holes merge, the gravitational waves they emit are not always perfectly symmetrical. If more energy is radiated in one direction, the merged black hole receives a recoil, like the gentle push of a jet engine, though on a cosmic scale. In extreme cases, this recoil can be strong enough to eject the black hole from the centre of its galaxy entirely. Such an object would drift through intergalactic space, carrying with it perhaps a small cluster of stars that had been orbiting nearby. These displaced giants are rare, but they offer a fascinating glimpse into how energetic and dynamic the universe can be. Despite their dramatic origins, rogue black holes are not especially dangerous on a galactic scale. Space is vast beyond everyday comprehension. The distances between stars are so large that even objects moving at high speeds rarely come close to one another. A black hole wandering through the Milky Way would be unlikely to pass near any planetary system, and even if it did, its gravitational influence would be noticeable only at relatively short distances. Gravity weakens rapidly with distance, following the inverse square law. Far away, a black hole's pull is no stronger than that of any other object with the same mass. Unless you approached very closely, it would not draw objects in dramatically, or sweep through space like a vacuum cleaner, as popular imagination sometimes suggests. Detecting rogue black holes is challenging precisely because they emit no light, and often have no companion star to reveal their presence. One of the most promising methods involves gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the light from that star, causing it to brighten temporarily. By carefully measuring the duration and characteristics of such brightening events, astronomers can estimate the mass of the intervening object. In recent years, some microlensing events have provided strong evidence for isolated black holes with masses several times that of the Sun drifting through the Milky Way. These detections are rare, but they confirm that rogue black holes are not merely theoretical possibilities. Another potential clue comes from the way a rogue black hole might interact with the sparse gas and dust in interstellar space. As it moves, it could slowly accrete a small amount of material, producing faint emissions detectable with sensitive instruments. Such signals would be extremely weak, but future telescopes may become capable of finding them. There is something quietly intriguing about the idea that our galaxy may contain millions of these invisible wanderers, relics of ancient stars moving silently through the darkness. Most of them will never encounter anything of significance. They will simply continue their journeys, orbiting the galaxy like distant, unseen planets in the grand gravitational field of the Milky Way. From a broader perspective, rogue black holes remind us that the universe is not static. Objects are constantly being rearranged by gravitational interactions. Stars are born, stars die, clusters disperse, galaxies merge, and black holes drift. Over cosmic timescales, motion is the rule rather than the exception. It's also interesting to consider how long a rogue black hole might wander. Without a companion or a dense environment to feed it, a black hole can persist almost unchanged for trillions of years. Hawking radiation will eventually cause it to evaporate, but for stellar mass black holes, that process takes far longer than the current age of the universe. In practical terms, a rogue black hole is nearly eternal, travelling through space long after the stars that formed it have faded. There is a certain quietness in that image, a solitary object moving through interstellar darkness, carrying within it the collapsed core of a star that once shone brightly. It is a reminder that the universe preserves its history in many forms, some luminous, some invisible. Rogue black holes also play a role in shaping their surroundings, though usually in subtle ways. As they pass through regions of gas or near small clusters of stars, their gravity can slightly alter orbits, stir material, or capture occasional objects into temporary trajectories. These interactions are gentle compared to the dramatic feeding of active galactic nuclei, but they still contribute to the slow evolution of galactic structures. Astronomers are continuing to search for more examples of these wandering objects. Large surveys that monitor millions of stars for microlensing events, along with future space telescopes designed to measure stellar positions with extraordinary precision, are expected to reveal many more isolated black holes in the coming years. Each discovery helps refine estimates of how common these objects are and how they are distributed throughout the galaxy. It may turn out that rogue black holes are among the most numerous stellar remnants in existence, quietly outnumbering neutron stars and white dwarfs in certain regions. There is also the possibility that some intermediate mass, or even larger black holes, could become rogues through gravitational recoil or galaxy mergers. Such objects would be rare, but their existence would offer valuable insights into the dynamics of galaxies and the behaviour of gravitational waves during mergers. As we continue moving through the different kinds of black holes, it becomes clear that size and origin are only part of the story. The behaviour of a black hole also depends on what surrounds it, whether it is isolated in the dark or actively feeding on nearby matter. In most of the situations we've talked about so far, black holes have been quiet. They sit in darkness, influencing their surroundings through gravity, sometimes drifting alone, sometimes orbiting companions, often doing very little that would attract attention from across the vast distances of space. But there are periods in the life of a galaxy when a black hole is anything but quiet. Under the right conditions, a black hole can become the engine of one of the brightest and most energetic phenomena in the universe. These luminous objects are called Quazers. The name itself comes from quasi-stellar radio source, a term astronomers began using in the 1960s when they first detected strange star-like points of light that emitted powerful radio waves. At first, no one was sure what they were. Through telescopes, they appeared small, almost like ordinary stars, yet their spectra revealed that they were extraordinarily distant, far beyond the boundaries of our galaxy. And if they were that distant, their brightness implied something astonishing. Each one was producing more energy than an entire galaxy of hundreds of billions of stars. That realization was deeply puzzling. How could a region so small produce so much energy? The answer, discovered gradually over years of observation and theory, was that quasars are powered by supermassive black holes surrounded by enormous disks of infalling matter. The black hole itself remains dark, but the gas spiraling inward becomes heated to extreme temperatures, radiating vast amounts of energy before it crosses the event horizon. To understand why this process is so powerful, it helps to compare it with something more familiar. In a star, energy comes from nuclear fusion, where light elements combine to form heavier ones, releasing energy in the process. Fusion is remarkably efficient by everyday standards, but even so, it converts less than 1% of the mass involved into energy. Accretion onto a black hole can be far more efficient. As matter falls inward, gravitational energy is converted into heat and radiation. Depending on the details, as much as 10% or more of the infalling mass can be converted into energy before the material disappears beyond the event horizon. That is an enormous efficiency, making black hole accretion one of the most powerful energy-producing processes known in nature. This energy is released in several forms. The accretion disk itself glows intensely, often producing ultraviolet and X-ray radiation. Magnetic fields threaded through the disk can channel some of the material into narrow jets that shoot outward at nearly the speed of light, extending for thousands or even millions of light years. These jets can be detected in radio waves, visible light, and other parts of the spectrum, creating some of the most striking images in astronomy. Yet despite all this activity, the region producing the energy is surprisingly small. Observations of quasar variability, the way their brightness changes over time, show that the emitting regions must be only light days or light weeks across, tiny compared to the size of the host galaxy. It is extraordinary to think that something smaller than our solar system can outshine an entire galaxy. Quasars are not permanent features. They represent a phase in the life of a galaxy, a period when large amounts of gas and dust are falling toward the central black hole. This can happen during galaxy mergers, when gravitational interactions disturb vast clouds of gas, sending them spiraling inward. It can also occur when instabilities within a galaxy channel material toward the center. During these periods, the black hole grows rapidly, consuming matter and releasing energy. Over time, however, the supply of gas diminishes and the quasar fades. The galaxy settles into a quieter state, leaving behind a supermassive black hole that may remain dormant for millions or billions of years until new material becomes available. This idea helps explain why quasars are more common in the distant universe than in the nearby one. When we look far away, we are looking back in time, to an era when galaxies were younger, mergers were more frequent, and abundant gas provided fuel for active black holes. In the present-day universe, most supermassive black holes are relatively quiet, including the one at the center of our own galaxy. There is something calming in that thought. The universe has its active periods and its quiet ones, just as living systems do. Activity rises and falls, sometimes dramatically, but not forever. Another fascinating feature of quasars is the structure of their surroundings. The accretion disk is often surrounded by a thick donut-shaped cloud of gas and dust called a torus. Depending on the angle from which we observe the system, this torus can obscure some of the light from the inner regions, causing quasars to appear in different forms, such as Seyfert galaxies or radio galaxies. In many cases, these different categories are not fundamentally different objects, but simply the same phenomenon viewed from different perspectives. This realization was an important step in understanding active galactic nuclei, the broader class of energetic galactic centers that includes quasars. It showed that much of the diversity observed in these objects arises from orientation and environment rather than entirely different physical processes. The jets produced by some quasars are among the most impressive structures in the cosmos. Narrow beams of charged particles guided by magnetic fields can travel vast distances into intergalactic space. As they move, they interact with the surrounding medium, creating enormous lobes of radio emission that can extend far beyond the visible boundaries of the host galaxy. These jets are not continuous streams in the ordinary sense, but flows of plasma moving at relativistic speeds, close to the speed of light. Their formation is still an area of active research, but most models involve the extraction of rotational energy from the black hole or its accretion disk, mediated by strong magnetic fields. It is remarkable that something as intangible as a magnetic field, combined with the rotation of space-time itself, can launch streams of matter across hundreds of thousands of light-years. Quasars also serve as valuable tools for studying the universe. Because they are so bright, they can be seen at enormous distances, allowing astronomers to probe the conditions of the early cosmos. Light from a distant quasar passes through clouds of gas on its way to Earth, and those clouds leave characteristic absorption lines in the quasar's spectrum. By studying these lines, scientists can learn about the composition, temperature, and motion of matter in the intergalactic medium billions of years ago. In this way, quasars act like cosmic backlights, illuminating structures that would otherwise be invisible. There is also a certain perspective to be gained from thinking about the timescales involved. The quasar phase of a galaxy may last tens or hundreds of millions of years, which is long compared to human history but short compared to the lifetime of galaxies. During that time, the central black hole can grow substantially, sometimes doubling or tripling its mass. Then the activity subsides, and the galaxy enters a quieter period, perhaps punctuated by occasional smaller outbursts as new material falls inward. It's interesting to imagine the Milky Way in such a phase. Billions of years ago, our galaxy's central black hole may have been far more active, shining brightly as matter fell into it. Evidence for past outbursts can be seen in enormous structures known as the Fermi bubbles, vast lobes of high-energy radiation extending above and below the galactic plane. These may be the remnants of activity that occurred millions of years ago, a faint echo of a more energetic past. Even today, Sagittarius, a star, occasionally produces small flares as bits of gas and dust fall inward. These events are tiny compared to the power of a true quasar, but they remind us that the processes are still there, waiting for the right conditions. Another point worth reflecting on is how the energy released by quasars affects their host galaxies. The radiation and outflows from the central region can heat surrounding gas, preventing it from cooling and forming new stars. In some cases, powerful winds driven by the quasar can push gas out of the galaxy entirely. This process, known as feedback, plays a crucial role in regulating galaxy growth. Without it, galaxies might form stars too rapidly, becoming far more massive than we observe. The black hole, despite occupying only a tiny fraction of the galaxy's volume, helps shape its evolution over billions of years. There is a kind of balance in that relationship. The galaxy feeds the black hole with gas, and the black hole, in turn, influences the galaxy, controlling how much of that gas remains available for star formation. Observations of quasars also reveal how rapidly black holes can grow under favourable conditions. Some of the most distant quasars, seen when the universe was less than 1 billion years old, already contain black holes with masses of billions of suns. Explaining how such enormous objects form so quickly remains one of the major challenges in astrophysics. Possible explanations include the direct collapse of massive gas clouds, very rapid accretion in dense environments, or the early formation of large seed black holes that later grew through mergers and accretion. Each possibility is being studied through simulations and observations, and future telescopes may help clarify which mechanisms were most important. There is also something quietly humbling about the scale of energy involved in quasars. The light from a single quasar can travel for billions of years, crossing vast stretches of space before reaching our telescopes. When we observe such an object, we are seeing it as it existed long before Earth formed, long before the sun began to shine. In a sense, quasars are not just distant in space, but distant in time, reminders of a younger universe filled with intense activity. And yet, despite their brightness and power, Quasers are temporary. Eventually the fuel runs low, the accretion disk fades, and the black hole returns to a quieter existence. The galaxy continues evolving, stars orbiting calmly, gas clouds drifting, the dramatic phase passing into history. That pattern, periods of activity followed by long stretches of quiet, seems to repeat throughout the cosmos. Far back in time, long before our Sun existed, long before the Milky Way had settled into its present shape, the universe looked very different. Galaxies were smaller and more irregular. Stars were forming at astonishing rates. Vast clouds of hydrogen and helium were collapsing under gravity, giving birth to the first generations of luminous objects that would begin to light the darkness left after the Big Bang. And somewhere within that early, crowded universe, the first black holes appeared. Some of them were probably the remnants of the very first massive stars, objects far larger than most stars forming today. Others may have formed through more direct collapses of enormous clouds of gas, bypassing the usual stages of stellar evolution. However they formed, these early black holes faced a universe rich in fuel. Gas was abundant, galaxies were still assembling, and mergers between young galaxies were common. Under such conditions, black holes could grow. What has puzzled astronomers for years is just how quickly some of them seem to have grown. Observations of distant quasars reveal black holes with masses of 1 billion suns or more, at times when the universe was less than 1 billion years old. To put that in perspective, the universe today is nearly 14 billion years old. These ancient black holes reached enormous sizes in less than 1/10 of that time. That is a surprisingly short period for such dramatic growth. To understand why this is puzzling, consider how black holes increase their mass. The primary mechanism is accretion, the gradual accumulation of matter falling inward. But as we discussed earlier, there is a practical limit to how fast this process can occur. As gas falls into a black hole and heats up, it emits radiation, and that radiation pushes outward on the inflowing material. This balance, known as the Eddington limit, sets a kind of maximum growth rate under normal conditions. If a black hole begins as a small stellar remnant, growing to billions of solar masses within a few 100 million years, becomes difficult to explain under this limit. Something about the early universe must have allowed faster growth, larger initial seeds, or both. One possibility is that the first black holes did not begin as small remnants at all. Instead, enormous clouds of gas in the earliest galaxies may have collapsed directly into black holes containing tens of thousands or even hundreds of thousands of solar masses. These so-called direct collapse black holes would have had a head start, allowing them to reach supermassive sizes more quickly. Another idea involves extremely rapid accretion in dense environments. In the early universe, gas was more plentiful and less enriched with heavy elements, which affected how it cooled and fragmented. Under certain conditions, large amounts of gas might have flowed steadily toward a central black hole, allowing it to grow faster than typical limits would suggest. Mergers may also have played a significant role. Young galaxies collided and merged frequently, bringing their central black holes together. Each merger added mass, gradually building larger and larger objects. Over hundreds of millions of years, repeated mergers could produce black holes of extraordinary size. Yet even with these possibilities, many details remain uncertain. Astronomers continue to study the earliest quasars to learn more about how such rapid growth occurred. Each new observation provides clues, helping refine our understanding of the processes at work during cosmic dawn. Observing these ancient black holes is not easy, because they are so distant. The light we see from them has travelled for billions of years, stretched to longer wavelengths by the expansion of the universe. Modern telescopes, both on Earth and in space, are designed to detect this faint red-shifted light, allowing astronomers to peer back into the first billion years of cosmic history. When we observe one of these distant quasars, we are seeing it as it existed when the universe was young, long before our galaxy had taken its present form. The photons entering our telescopes tonight began their journey billions of years ago, crossing vast expanses of space before reaching us. There is something quietly awe-inspiring about that, a reminder of how deeply connected observation and time are in astronomy. These early black holes also provide insight into the environments in which the first galaxies formed. The radiation from quasars can ionize surrounding gas, affecting star formation and shaping the evolution of nearby structures. In this way, black holes were not merely byproducts of galaxy formation, but active participants in it, influencing the growth of galaxies from the very beginning. Another intriguing aspect of early black holes is their possible connection to the rionization of the universe, a period when ultraviolet radiation from the first stars and quasars ionized the neutral hydrogen filling space. Understanding how much quasars contributed to this process remains an active area of research, with astronomers studying the spectra of distant objects to trace the ionization state of intergalactic gas. The earliest black holes may also hold clues about the nature of dark matter and the formation of large-scale structure. By studying how these objects are distributed and how they grew, scientists can test models of galaxy formation and the behaviour of matter in the early universe. It's fascinating to realise that black holes, often thought of as endpoints, may actually have been among the earliest complex structures to form. Gravity, acting on small fluctuations in density, began shaping the universe almost immediately after the Big Bang, and black holes may have been part of that story from very early on. There is also a reflective perspective to consider. The oldest black holes have existed for nearly the entire history of the cosmos. They formed when the universe was young, and they have persisted through billions of years of change, witnessing the birth of countless stars, the merging of galaxies, and the gradual cooling of cosmic temperatures. If time could be experienced from their perspective, the entire history of the Milky Way would pass like a brief episode in an immensely long existence. And yet, even these ancient giants are not truly eternal. Over timescales far beyond anything we can easily imagine, Hawking radiation will slowly reduce their mass. Trillions upon trillions of years from now, long after the last stars have faded, even the largest black holes may begin to evaporate more rapidly, eventually disappearing in faint bursts of radiation. That distant future lies so far ahead that it feels almost abstract, but it reminds us that change is universal. Nothing in the cosmos remains exactly as it is forever. In the present era, astronomers are continuing to search for ever more distant quasars and early black holes, pushing observations closer to the beginning of time. New telescopes with greater sensitivity and resolution are revealing galaxies and black holes that formed when the universe was only a few 100 million years old, providing new data to test theories of cosmic evolution. Each discovery brings us a little closer to understanding how structure emerged from the nearly uniform conditions of the early universe, how gravity shaped matter into stars and galaxies, and how black holes grew alongside them. Time is one of those things we rarely question in everyday life. It moves forward at a steady pace, or at least it seems to. Minutes pass, hours pass, days turn into years, and the rhythm feels constant enough that we rarely stop to wonder whether time itself might behave differently elsewhere in the universe. But gravity changes time. This is not a metaphor or a poetic way of speaking. It is a measured physical effect, confirmed by experiments and used in practical technology every day. And near black holes, where gravity becomes extraordinarily strong, the flow of time changes in ways that are both subtle and profound. To understand how this happens, it helps to begin with something familiar. Even here on Earth, time does not pass at exactly the same rate everywhere. Clocks at higher altitudes, farther from Earth's centre, tick ever so slightly faster than clocks at sea level. The difference is tiny, far too small to notice without extremely precise instruments, but it is real. Satellites in orbit experience this effect as well, and their onboard clocks must be corrected for it in order for systems like GPS to work accurately. These small differences arise because gravity affects the passage of time. The stronger the gravitational field, the more time slows relative to regions where gravity is weaker. Near a black hole, this effect becomes dramatic. Imagine a clock gradually approaching the event horizon of a black hole. To an observer far away, that clock would appear to tick more and more slowly as it descended deeper into the gravitational field. The light from it would also become stretched to longer wavelengths, shifting toward red, a process known as gravitational redshift. Eventually, the clock would appear to freeze, its ticks becoming farther and farther apart until they seemed to stop entirely. From the distant observer's perspective, the clock would never quite cross the event horizon. Its image would fade and redden, becoming dimmer and dimmer, as if time itself were stretching to infinity at the edge of the black hole. But the experience of the clock, or of an astronaut falling with it, would be very different. From that perspective, time would feel perfectly normal. The astronaut would cross the event horizon in a finite amount of time, noticing nothing especially dramatic at the moment of crossing, at least in the case of a sufficiently large black hole where tidal forces near the horizon are relatively gentle. This difference between perspectives is one of the most fascinating aspects of relativity. Time is not absolute. It depends on the observer, on their motion, and on the gravitational field in which they find themselves. It may help to think of time not as a universal river flowing at the same speed everywhere, but as part of the fabric of space-time itself, something that can stretch and compress under the influence of gravity. Near a black hole, that stretching becomes extreme. If you could somehow hover just outside the event horizon of a supermassive black hole and then return to a distant region of space, you might find that far more time had passed in the outside universe than for you. Minutes or hours near the black hole could correspond to years, decades, or even longer elsewhere, depending on how close you were to the horizon and how massive the black hole was. This is not science fiction. It is a prediction of general relativity, confirmed in less extreme situations and supported by extensive theoretical work. There is something quietly humbling about this idea. Time, which feels so steady and universal in our daily lives, turns out to be flexible, shaped by gravity and motion. The universe does not share a single universal clock. Instead, every object carries its own measure of time, shaped by the path it follows through space-time. Black holes represent one of the most extreme environments where this effect can be observed in theory. The slowing of time near a black hole also affects the behavior of matter and radiation. Light emitted from near the event horizon loses energy as it climbs out of the gravitational well, shifting toward longer wavelengths. Processes that occur rapidly near the horizon appear slower and slower to distant observers. This effect plays an important role in the way accretion disks and other phenomena near black holes are observed. The light we see carries not only information about temperature and motion, but also about the curvature of space-time itself. There is another aspect of time near black holes that is equally intriguing, involving the paths that objects can take through space-time. In ordinary circumstances, the future lies ahead of us in time, and the past lies behind. We move forward along our world line, unable to turn around and travel backward. Inside a black hole, according to classical general relativity, the structure of space-time changes in such a way that all possible paths lead inward toward the singularity. The singularity lies not merely in space but in the future of anything that crosses the event horizon. Just as we cannot avoid moving into the future, anything inside the horizon cannot avoid moving toward the centre. This idea can feel difficult to picture, because it challenges our everyday intuition about space and time as separate things. But in relativity, space and time are intertwined, and gravity can tilt the directions of both. Another way to think about this is to imagine space-time as a landscape of paths, where gravity reshapes the terrain. Near a black hole, the paths that lead outward gradually disappear, leaving only those that lead inward. Time itself, in a sense, points toward the singularity. The deeper physicists study these effects, the more questions arise. What happens to time at the singularity itself? Do the laws of physics as we know them continue to apply, or does a new description become necessary? These questions remain unanswered, because the singularity represents a boundary of our current understanding. General relativity predicts its existence, but quantum mechanics suggests that a more complete theory is needed to describe what truly happens under such extreme conditions. Black holes also raise intriguing questions about the relationship between time and information. When matter falls into a black hole, information about its structure and composition seems to disappear from the observable universe. Yet quantum theory suggests that information cannot be destroyed. This apparent contradiction, known as the black hole information paradox, has been the subject of decades of research. Proposed solutions involve ideas such as Hawking radiation carrying away information, or the possibility that information is preserved in subtle correlations on the event horizon itself. These are deep and complex topics, but at their heart lies a simple and profound realization. Black holes are not just objects in space. They are laboratories for understanding time itself. There is also a more reflective perspective to consider. The universe is filled with processes that unfold over immense timescales. Stars live for billions of years. Galaxies evolve over tens of billions. Black holes may persist for trillions or longer. Near a black hole, time for one observer can pass at a very different rate than for another, reminding us that time is not a universal measure but a local experience. If you imagine two observers, one far from a black hole and one near it, their lives would unfold at different rates relative to each other. When they reunited, one might find that the other had aged far more. This is sometimes called gravitational time dilation, and while the extreme version requires the intense gravity of a black hole, the principle applies everywhere, even here on Earth. Though the differences are so small we do not notice them. Black holes, in this sense, are magnifying glasses for the laws of physics. They take effects that exist everywhere and amplify them until they become impossible to ignore. Another interesting aspect involves the way rotating black holes affect time. As we discussed earlier, rotation drags space-time around with it. Near such a black hole, the paths of objects and the flow of time become intertwined in even more complex ways. Observers moving in different directions around the black hole can experience time differently, depending on their trajectories. These effects have been explored in theoretical studies and computer simulations, revealing a richness in the structure of space-time that goes far beyond our everyday experience. It is remarkable that all of this arises from a theory developed over a century ago. Einstein's equations, elegant and compact, describe how mass and energy shape space-time, and black holes represent one of the most dramatic predictions of those equations. And yet, the story is not complete. Physicists continue to search for a theory that unifies general relativity with quantum mechanics, a theory that would fully explain what happens to time and space at the smallest scales and highest energies. Black holes may hold the key to that unification. Their event horizons, their radiation, and their singularities bring together gravity, thermodynamics, and quantum theory in ways that no other objects do. There is also something quietly calming about reflecting on time in this way. Our daily lives are governed by clocks and schedules, by minutes and hours that seem to pass too quickly or too slowly depending on circumstances. But on cosmic scales, time flows in ways that are far more varied and subtle. Near a black hole, moments can stretch. In intergalactic space, billions of years can pass in silence. The universe is not in a hurry. It unfolds at its own pace, shaped by gravity and expansion, by the slow dance of galaxies and the quiet persistence of stars. And even the most extreme environments where time itself bends and stretches are governed by consistent laws, predictable and understandable, at least in part. At some point, almost everyone who hears about black holes begins to wonder the same thing. What actually happens inside one? It's a natural question. We've talked about how black holes form, how they grow, how they merge, and how they influence the galaxies around them. We've explored how gravity changes time and how light behaves near the event horizon. But the interior remains in many ways the most mysterious part of all, and the reason is simple. By definition, no information from inside the event horizon can reach us. Whatever happens there is hidden, not just difficult to observe, but fundamentally beyond direct observation. That boundary, the event horizon, is not just a physical threshold. It is also a boundary of knowledge, at least for now. Still, physics allows us to say quite a lot about what should happen, at least according to our current theories, and the story begins with understanding the event horizon itself. It's easy to imagine the event horizon as a kind of surface, like the surface of a planet or a star, but that picture can be misleading. There is no solid barrier there, no sudden wall or glowing line in space. The event horizon is simply the point where the escape velocity equals the speed of light. Cross that boundary, and every possible path through space-time leads inward. If you are falling toward a sufficiently large black hole, you might not notice anything special at the moment you cross the horizon. There would be no flash, no jolt, no sudden change in your local environment. The stars behind you would still shine, at least for a while, and the physics immediately around you would seem ordinary, aside from the increasing gravitational effects as you move deeper inward. This quiet crossing is one of the most surprising aspects of black holes. From far away, the event horizon seems dramatic, even absolute. But locally, it can be almost unremarkable. The real changes become more noticeable as you continue inward, because gravity does not simply pull, it stretches. Earlier we mentioned tidal forces, the difference in gravitational pull between one part of an object and another. Near a black hole, these differences can become enormous. Your feet, being closer to the centre, would feel a stronger pull than your head. Over time, this difference would stretch you along the direction of the gravitational field and compress you sideways, a process sometimes called spaghettification. The severity of this effect depends on the size of the black hole. Near a small stellar mass black hole, tidal forces near the event horizon are extremely strong, and stretching would begin well before crossing it. Near a supermassive black hole, however, the horizon is so large that tidal forces there can be relatively gentle, at least initially. You might cross the horizon without experiencing extreme stretching until much later. Eventually, though, the tidal forces would become overwhelming. As you move deeper inward, the curvature of space-time would grow stronger and stronger. Paths that once allowed you to move outward would no longer exist. The structure of space-time itself would guide every possible motion toward the centre. And that brings us to the singularity. In classical general relativity, the singularity is a point, or in the case of a rotating black hole, a ring, where density becomes infinite and the known laws of physics break down. It is not merely a place of extreme conditions, but a place where our mathematical descriptions no longer work. It's important to understand what this means. When physicists say that density becomes infinite, they're not necessarily claiming that infinity exists in a physical sense. Rather, it means that the equations we use to describe gravity and matter produce results that no longer make sense, indicating that the theory is incomplete under those conditions. Most scientists believe that a full theory of quantum gravity, one that unifies general relativity with quantum mechanics, will eventually provide a more accurate description of what happens in these extreme environments. But for now, the singularity remains a boundary of understanding. There is something quietly humbling about that. After centuries of scientific progress, there are still places in the universe where our knowledge reaches its limits. Another fascinating aspect of black hole interiors involves the nature of time and space. Outside a black hole, we're used to thinking of time as something separate from space, a dimension that moves steadily forward. Inside the event horizon, the roles of space and time begin to change in ways that are difficult to visualize. In a sense, the singularity lies in the future of anything that crosses the horizon. Just as we cannot avoid moving into the future, an object inside a black hole cannot avoid moving toward the singularity. It is not merely falling through space, it is moving through space-time in a direction that inevitably leads inward. This idea can feel abstract, but it reflects the deep connection between space and time in Einstein's theory. Gravity does not simply pull objects through space, it reshapes the geometry of space-time itself, altering the directions that motion can take. There are also theoretical possibilities, still debated and explored, about what might exist inside black holes beyond the classical picture. Some solutions to Einstein's equations suggest the existence of wormholes, hypothetical tunnels connecting distant regions of space-time. Others propose that quantum effects might prevent the formation of true singularities, replacing them with extremely dense but finite structures. These ideas remain speculative, but they illustrate how black holes continue to challenge and expand our understanding of physics. Another deep question concerns information. When matter falls into a black hole, it carries information about its structure, composition, and quantum state. According to classical general relativity, that information disappears behind the event horizon, seemingly lost forever. But quantum mechanics suggests that information cannot be destroyed. This conflict, known as the black hole information paradox, has been one of the central puzzles in theoretical physics for decades. Stephen Hawking's discovery that black holes emit radiation added a new layer to this puzzle. If black holes can evaporate over time, what happens to the information contained in the matter that fell into them? Does it escape in some subtle form? Is it preserved on the event horizon? Or does it remain in some hidden way that we do not yet understand? Many proposed solutions exist, involving ideas such as holographic principles, where information about a volume of space is encoded on its boundary, or the possibility that correlations in Hawking radiation carry information outward. These are complex and ongoing areas of research, but they highlight how black holes sit at the intersection of some of the deepest questions in physics. It's also interesting to reflect on how different observers perceive events near the event horizon. To someone falling in, the crossing happens in a finite time, and the journey inward continues. To a distant observer, the infalling object appears to slow down, fade, and never quite cross the horizon. Both perspectives are valid within the framework of relativity, even though they seem to contradict each other. This duality is one of the many ways black holes challenge our everyday intuition. There is also the question of whether anything could survive inside a black hole, even briefly. The answer depends on the size of the black hole and the nature of the object falling in. Near a supermassive black hole, tidal forces at the horizon may be mild enough that a spacecraft could cross without immediate destruction. But deeper inside, the increasing curvature of space-time would eventually tear apart any known form of matter. Even light cannot escape, but light still exists inside, travelling along paths that lead inevitably inward. The interior of a black hole is not empty. It contains whatever matter and radiation have fallen in, compressed and transformed in ways we cannot yet fully describe. Some physicists have speculated about the possibility that black holes might contain entire regions of space-time, perhaps even new universes, hidden from our own. These ideas are highly speculative, but they arise naturally from certain solutions of the equations of general relativity. Whether they have any connection to reality remains unknown. What is certain is that black holes represent the most extreme environments known, places where gravity, quantum mechanics, and thermodynamics all play crucial roles. They are not merely exotic objects, but keys to understanding the fundamental nature of the universe. There is something quietly profound about that. Objects once considered purely theoretical, once thought too strange to exist, are now observed and studied, guiding us toward deeper insights about space, time, and reality itself. And yet, even with all we have learned, the interior of a black hole remains in many ways beyond our reach. It is a reminder that science is not only about answers but also about questions, about exploring the edges of knowledge and gradually pushing them outward. Perhaps future theories will reveal what truly happens at the singularity, or whether singularities exist at all. Perhaps new observations will uncover phenomena we have not yet imagined. The story is still unfolding, and the universe still has much to teach us. As our exploration continues, it becomes clear that black holes are not isolated curiosities but part of a broader cosmic pattern. They form, evolve, merge, and influence their surroundings, playing a role in shaping galaxies and the large-scale structure of the universe itself. After exploring so many different kinds of black holes, from the remnants of dying stars to giants weighing billions of suns, from hypothetical microscopic ones to ancient objects that may have formed near the beginning of time, a quiet question naturally begins to form. Why are there so many kinds of black holes at all? At first, it might seem as if there should be only one type. After all, a black hole is defined by a simple condition: enough mass compressed into a small enough space that not even light can escape. The idea itself is straightforward, and yet when we look closely at the universe, we find an entire spectrum of black holes, each shaped by different origins, environments, and histories. The reason for this diversity lies in something both simple and profound. The universe itself is diverse. Stars are born with different masses, rotate at different speeds, and live in different surroundings. Galaxies collide, clusters evolve, and gas flows in complex patterns across cosmic time. Gravity acts everywhere, but it acts on matter that is never perfectly uniform. Small differences at the beginning lead to large differences over billions of years. Black holes, in this sense, are not exceptions to the universe's variety. They are products of it. Consider stellar mass black holes. These form when massive stars reach the ends of their lives and collapse under their own gravity. The mass of the original star, the rate at which it rotated, the presence or absence of a companion, and the composition of the surrounding gas all influence the black hole that remains. Some are heavier, some lighter, some spin rapidly, others more slowly. Move outward in scale, and intermediate mass black holes may form through repeated mergers in dense clusters, or from the collapse of unusually massive stars in the early universe. The pathways differ, but the underlying process is still gravity gathering matter over time. At the centres of galaxies, supermassive black holes grow through accretion and mergers, shaped by the histories of their host galaxies. Galaxies that collide frequently may produce larger central black holes. Galaxies with abundant gas may feed their black holes more efficiently. Over billions of years, these differences accumulate, producing the wide range of masses we observe. Ultramassive black holes represent the most extreme outcomes of these processes, objects that grew for immense stretches of time, sometimes in environments rich in gas, sometimes through repeated mergers in crowded clusters of galaxies. Then there are primordial black holes, if they exist, which would represent an entirely different origin story. Not the death of stars or the growth of galaxies, but the collapse of dense regions in the earliest moments of cosmic history. These would be relics of the young universe itself, shaped by conditions that no longer exist today. Even micro-black holes, though hypothetical, arise naturally from the same physical laws when applied at very small scales. They remind us that the equations of gravity do not care about size. They apply equally to the very large and the very small. And beyond size and origin, there are other ways black holes can differ. Some spin rapidly, dragging space-time around them. Some may carry tiny amounts of electric charge. Some exist in pairs, spiraling together over millions of years, while others drift alone through interstellar space, silent and solitary. All of this variety emerges from the same underlying principles: gravity, motion, and the passage of time. There is something deeply reassuring about that. The universe does not need special rules to produce extraordinary phenomena. The same laws that cause an apple to fall or the moon to orbit Earth also produce quasars, gravitational waves, and the shadows of black holes in distant galaxies. Complexity arises naturally when simple rules operate over vast scales. Black holes also reveal something important about the history of the universe. Each one carries, in a sense, a record of the processes that formed it. The mass of a black hole tells us about the matter that collapsed or merged. Its spin carries clues about past accretion or collisions. Its environment reveals the conditions of the galaxy or cluster in which it resides. By studying black holes, astronomers are not just learning about these objects themselves. They are learning about stars, galaxies, and the evolution of the cosmos. For example, the existence of supermassive black holes in nearly every large galaxy suggests that black hole growth and galaxy formation are closely linked. The discovery of ancient quasars tells us that massive structures formed earlier than once expected. Observations of gravitational waves reveal how often black holes merge and how common different types of stellar remnants are. Each new piece of data adds to a larger picture, a picture of a universe that is dynamic, evolving, and interconnected. Another lesson from black holes concerns the nature of space and time. These objects show us that space-time is not rigid but flexible, shaped by mass and energy. They demonstrate that time can slow, that light can bend, and that the geometry of the universe can become so curved that entire regions are cut off from the rest. These are not merely curiosities, they're clues about the fundamental structure of reality. Black holes also bring together some of the deepest areas of physics. General relativity describes their large-scale behaviour, while quantum mechanics becomes important near their horizons and in the process of Hawking radiation. Thermodynamics appears in the form of black hole temperature and entropy. Few other phenomena connect so many branches of science in such a direct way. It is possible that understanding black holes more fully will lead to breakthroughs in our understanding of gravity, quantum theory, and the origin of the universe itself. There is also a more reflective way to think about this diversity. The universe is not uniform or repetitive. It is creative, in the sense that simple laws produce an astonishing range of structures and phenomena. Stars differ, planets differ, galaxies differ, and black holes differ. Variety is not an exception. It is the natural outcome of time and complexity. When we look up at the night sky, we see points of light that appear calm and unchanging, but behind that stillness lies a history of formation, collapse, collision, and transformation. Black holes are part of that history, silent witnesses to the lives and deaths of stars, the merging of galaxies, and the slow unfolding of cosmic time. It is also worth remembering that our understanding of black holes is still evolving. Only a few decades ago, their existence was uncertain. Today we can detect their mergers, measure their spins, and even image the glowing matter at the edge of their event horizons. Future observations will almost certainly reveal new kinds of black holes, new behaviours, and new connections to other areas of physics. The story is far from complete, and perhaps that is the most comforting thought to carry with you. The universe is not a finished book, but an unfolding one. There are still discoveries to be made, still questions to be asked, still mysteries waiting quietly in the darkness. Somewhere out there, black holes of many kinds are forming, merging, drifting, and slowly evolving. Part of a cosmos that is vast, patient, and endlessly fascinating. And as we continue to explore and to listen, to observe and to wonder, we become part of that story too. Participants in a long tradition of curiosity that stretches from the first stargazers to the astronomers of today, and onward into a future where the quiet secrets of the universe will keep revealing themselves, one gentle discovery at a time.